Long before Tyrannosaurus rex stalked prehistoric plains or pterosaurs soared through ancient skies, Earth was a realm so hostile, so alien, that would kill most modern life within moments. For nearly 4 billion years before the first dinosaur drew breath, our planet endured catastrophes that make extinction events look mild. Oceans that boiled away, atmospheres laced with poison, ice sheets that entombed the entire globe, and creatures so bizarre they seem ripped from science fiction nightmares. Giant scorpions prowled carboniferous swamps. Armored fish with guillotine jaws ruled Devonian seas. And during the Permian period's final days, 90% of all species vanished in Earth's worst mass extinction, a cataclysm that rewrote the rules of life itself. This is the untold story of our planet's most extreme chapter, the 4 billion years of violence, transformation, and evolution that sculpted the world dinosaurs will inherit. What you're about to discover will reshape how you see our planet's entire history. Let's dive in. The planet we call home began as violence incarnate. 4.6 billion years ago, in a swirling disk of gas and dust orbiting a newborn star, countless fragments of rock and metal collided with increasing fury. Each impact released tremendous energy, welding material together through sheer force. Within perhaps 50 million years, the geological eye blink, these collisions had assembled a sphere roughly the size of modern Earth, though no observer would recognize it. This was the beginning of the Hadean Aeon, named deliberately after the Greek underworld, and the comparison wasn't melodramatic. Early Earth was genuinely hellish, a realm where the very concept of a stable surface remained impossible for hundreds of millions of years. The mechanisms heating this infant world operated on scales difficult to comprehend. Gravitational compression alone generated immense temperatures as material collapsed inward, with denser elements like iron sinking toward the core, while lighter silicon-rich compounds rose. Radioactive decay of unstable isotopes, far more abundant in the early solar system than today, pumped additional heat into Earth's interior. But the most dramatic source came from above. Asteroid impacts, some involving objects hundreds of kilometers across, struck with such force that they temporarily liquefied vast portions of the surface. The energy released by these collisions prevented rock from solidifying in any meaningful way. Convection currents in the mantle constantly brought molten material upward while dragging cooling rock back down into magmatic seas. Earth's surface churned in perpetual flux. Scientists reconstructing this epic face a fundamental challenge. Almost no physical evidence survived. The oldest intact rock formations on Earth, found in Quebec's Novogedic Greenstone Belt, date back approximately 4.28 billion years, leaving the earliest 300 million years of planetary history largely blank. Plate tectonics has recycled nearly all original crustal material through subduction over the eons. Yet researchers aren't working completely blind. Tiny crystals called zircons, barely larger than grains of sand, have proven extraordinarily resilient. These minerals form in molten rock and incorporate uranium atoms into their crystal structure, which allows precise radiometric dating. More importantly, zircons resist chemical alteration and can survive even when their parent rocks have long since vanished. The most famous collection of these ancient survivors comes from Jack Hills in Western Australia. They're embedded in metamorphosed sedimentary rocks deposited roughly 3 billion years ago. Scientists have discovered zircon grains dated to 4.4 billion years ago, pushing back into the heart of the Hadean. The zircons themselves are older than the rocks containing them, having eroded out of even more ancient formations that no longer exist. These crystals represent our only direct physical samples from Earth's first 500 million years. What they reveal has forced geologists to revise their understanding of early planetary conditions. Analysis of oxygen isotope ratios within these Hadean zircons suggests something unexpected. Oxygen exists in 3 stable forms: oxygen-16, oxygen-17, and oxygen-18, and their relative proportions shift through processes like evaporation and condensation. The ratio of lighter oxygen-16 to heavier oxygen-18, measured as delta-18O, serves as a proxy for ancient temperatures and the presence of liquid water. When researchers examined Jack Hill's zircons dated to 4.4 billion years ago, The isotope signatures indicated formation temperatures probably below 100 degrees Celsius. This implies that stable continental crust and liquid water oceans may have existed far earlier than previously imagined, perhaps within just 150 million years of Earth's formation. The planet had apparently transitioned from a globe-spanning ocean of magma to something resembling a solid surface with genuine oceans faster than anyone expected. Yet even if localized patches of crust and water existed earlier than once thought, the Hadean remained fundamentally inhospitable. The sun burned roughly 30% dimmer than today, yet geological evidence suggests Earth maintained temperatures warm enough to sustain liquid water, a puzzle known as the faint young sun paradox. The solution likely involved atmospheric composition. With minimal to no free oxygen and abundant volcanic outgassing, the early atmosphere probably contained enormous concentrations of carbon dioxide and water vapor, both potent greenhouse gases. Some models suggest carbon dioxide levels reached 10 to 2,500 times modern concentrations, creating a thick blanket that trapped heat and prevented the planet from freezing despite reduced solar luminosity. Methane may have played a role as well, though determining precise gas ratios from this distant era remains challenging. The bombardment that characterized the Hadean came in distinct phases. For the first several hundred million years, impacts occurred as remnant planetesimals, the building blocks of planets, continued clearing from the inner solar system. Earth's growing mass attracted increasingly large objects through gravitational pull. Some collisions involved bodies the size of small planets. The most catastrophic impact of all occurred approximately 4.5 billion years ago, when an object roughly the size of Mars, sometimes called Theia, struck Earth at an oblique angle. The energy released vaporized vast quantities of rock from both bodies. The impact liquefied much of Earth's mantle and ejected enormous volumes of debris into orbit. This material eventually coalesced through gravitational attraction to form the Moon. Evidence for this giant impact hypothesis comes from multiple sources: the Moon's unusually large size relative to Earth, its low iron content compared to Earth's iron-rich core, and oxygen isotope ratios in lunar samples that match Earth's composition almost exactly, suggesting they formed from the same material. For perhaps several million years after the moon-forming impact, Earth remained covered by an ocean of molten rock hundreds to thousands of kilometers deep. Temperatures at the surface may have exceeded 1,500 degrees Celsius, hot enough to vaporize lead. The planet would have glowed a dull red visible from space, radiating heat into the void. Water that had been delivered by early comet and asteroid impacts likely boiled into the atmosphere, creating a steam envelope of crushing pressure. Only gradually, as impacts decreased in frequency and intensity, could the magma ocean begin to cool and crystallize. Minerals with high melting points solidified first, forming the earliest fragments of crust. These protocontinents likely resembled the basaltic plains visible on the Moon or Mars more than modern continental crust, which is richer in lighter elements like silicon and aluminum. Around 4.1 to 3.8 billion years ago, the exact timing remains debated, Earth may have experienced an uptick in bombardment known as the Late Heavy Bombardment. This hypothesis emerged from studies of lunar craters and rock samples returned by Apollo missions. Moon rocks dated to this narrow window showed extensive evidence of impact melting, suggesting a surge in collisions struck the inner solar system. If this bombardment occurred, gravitational interactions between Jupiter and Saturn migrating in the outer solar system may have destabilized asteroid orbits, sending swarms of debris careening inward toward the terrestrial planets. Earth, with its stronger gravity, would have suffered far more impacts than the Moon. Recent analysis using lunar crater data from NASA missions suggests this period saw impact rates potentially 100 times higher than background levels, though some researchers argue the spike may have been less dramatic or represented the tail end of steadily declining bombardment rather than a discrete event. The consequences for early Earth would have been severe. Large impacts, those involving asteroids 10 kilometers across or greater, released enough energy to vaporize entire oceans temporarily. The vapor would have formed a super-dense steam atmosphere that gradually recondensed over thousands of years, raining back down in deluges lasting centuries. Each time liquid water accumulated and potentially created habitable conditions, another massive collision reset the clock. Any protocontinental crust that formed could be shattered and remelted. If life somehow emerged during a calm interval, giant impacts may have repeatedly sterilized the surface, forcing any surviving organisms to shelter in deep-sea hydrothermal vents or kilometers beneath the seafloor where temperatures remain stable. Some scientists have suggested that the late heavy bombardment may have paradoxically aided life by delivering organic compounds and volatiles like water and carbon, though this remains speculative. By approximately 4 billion years ago, bombardment had finally waned to levels where the surface could stabilize. Volcanic activity remained intense, with heat flowing from Earth's interior far more vigorously than today, due to higher concentrations of radioactive elements and residual heat from formation. The atmosphere, derived from volcanic outgassing, lacked oxygen entirely and consisted primarily of nitrogen, carbon dioxide, water vapor, and likely methane and ammonia. Ultraviolet radiation from the sun struck the surface with full force, unfiltered by any ozone layer since ozone requires oxygen to form. The oceans, assuming they existed persistently by this point, would have been acidic from dissolved carbon dioxide forming carbonic acid. No ozone meant no protection from UV radiation for anything existing in shallow water or on land. The Hadean Eon closed around 4 billion years ago without any dramatic marker. Geologists simply define its end as the age of the oldest well-preserved rock formations. By that boundary, Earth had transformed from a hellscape of colliding debris and magma oceans into something more recognizable, a planet with solid crust, liquid water, and an atmosphere, albeit one profoundly different from today. Yet calling it recognizable stretches the term. Temperatures may have ranged from near boiling in some regions to near freezing in others. Volcanism reshaped the surface constantly. The day lasted perhaps 6 to 8 hours, since the moon orbited much closer and tidal forces had not yet slowed Earth's rotation. And the chemistry of atmosphere and ocean remained so alien that any modern organism transported back would die within moments. The stage was set for the next phase, the Archean Eon, when Earth's hellish conditions would persist, but life itself would emerge to transform the planet forever. The distinction between recognizing Earth had water and claiming it was hospitable requires emphasis. Even if oceans existed by 4 billion years ago, their chemistry would have been radically different from modern seas. The pH likely ranged somewhere between 6.4 and 7.8, reasonably neutral by our standards, but dissolved iron concentrations were vastly higher than today. With no atmospheric oxygen to oxidize it, ferrous iron released from hydrothermal vents and submarine volcanism remained soluble in seawater, giving the oceans a murky, greenish tint. Dissolved carbon dioxide created carbonic acid, while sulfur compounds from volcanic gases contributed additional acidity in certain regions. The absence of complex life meant no biological buffering systems existed to regulate ocean chemistry through processes like shell formation or organic carbon burial at modern scales. Volcanic activity dominated the late Hadean landscape far more intensely than anything witnessed in recorded human history. Earth's interior contained significantly more heat from radioactive decay and from the residual energy of formation. Mantle convection operated more vigorously, driving faster tectonic processes. Evidence from later Archean rocks, which preserves some record of these conditions, suggests oceanic crust formed and recycled much more rapidly. Volcanic islands and submarine plateaus erupted constantly, releasing massive volumes of gases into the atmosphere and oceans. The chemical composition of these emissions, primarily water vapor, carbon dioxide, nitrogen, sulfur dioxide, and smaller amounts of methane and ammonia, constructed the atmosphere that would persist into the Archean. This was a reducing atmosphere, meaning chemical reactions favored the formation of reduced compounds rather than oxidized ones. Any free oxygen produced through processes like ultraviolet photodissociation of water vapor was quickly consumed by reacting with reduced gases like methane or with iron dissolved in the oceans and exposed in rocks. Temperature regulation on this early Earth operated through the carbonate-silicate cycle, a negative feedback mechanism that still functions today but would have worked more rapidly in the Hadean and Archean due to higher volcanic activity. When atmospheric carbon dioxide levels rose, surface temperatures increased through greenhouse warming. Warmer temperatures accelerated the weathering of silicate rocks, which consumed carbon dioxide through chemical reactions that ultimately locked carbon into carbonate minerals deposited on the seafloor. If carbon dioxide levels dropped too low and temperatures fell, weathering slowed, allowing volcanic outgassing to replenish atmospheric carbon dioxide and restore warmth. This thermostat effect likely prevented runaway freezing despite the dim Young-Sunday climate models incorporating estimated Hadean conditions suggest that with carbon dioxide concentrations between 10 and 2,500 times present atmospheric levels, along with possible contributions from methane and other greenhouse gases, average surface temperatures could have remained between 0 and 40 degrees Celsius, a range that accommodates liquid water. The length of a Hadean day differed dramatically from modern experience. When the Moon first formed from the debris of the Theia impact, it orbited at a distance of perhaps 22,000 kilometers, compared to the current 384,000 kilometers. Gravitational forces at this proximity raised enormous tides in Earth's still molten or newly solidified crust, and the interaction produced intense tidal heating. More relevant to daily experience, tidal friction gradually transferred angular momentum from Earth's rotation to the Moon's orbit. This had two effects. Earth's rotation slowed, lengthening the day, while the Moon migrated outward to conserve angular momentum. In the late Hadean, days lasted perhaps 5 to 6 hours. The planet spun rapidly beneath a moon that appeared many times larger in the sky than today. Tidal forces were correspondingly stronger, creating massive ocean tides if liquid water existed, though some researchers suggest the early close proximity might have kept the oceans in a state of gravitational lock that prevented discrete tides as we understand them. Continental crust formation in the Hadean remains one of geology's most contentious topics. Modern continents consist primarily of granitic rocks, rich in silicon, aluminum, potassium, and sodium, which are less dense than the basaltic rocks dominating oceanic crust. Granite typically forms through complex processes involving partial melting of pre-existing crust, often requiring the presence of water and multiple cycles of melting and solidification. The Jack Hill zircons, with their oxygen isotope signatures suggesting interaction with liquid water, indicate that at least small amounts of granitic crust existed by 4.4 billion years ago. However, whether this represented true continents in any recognizable sense remains unclear. The material may have formed small, transient islands that were quickly recycled back into the mantle through vigorous early plate tectonics. Alternatively, it might have comprised a thin, discontinuous layer of more evolved crust floating atop a global ocean punctuated by volcanic islands. No consensus exists because direct evidence has been erased. By 4 billion years ago, as the Hadean drew to a close, Earth had stabilized enough that rocks from this era onward survive in the geological record. The Acasta gneiss in northwestern Canada, dated to 4.03 billion years, represents some of the oldest surviving continental material. Its existence proves that by the Hadean-Archean boundary, continental crust formation was well underway. The planet possessed oceans, an atmosphere, volcanic activity creating and recycling crust, and possibly the first stirrings of life, though evidence for life this early remains disputed and will be addressed in the following chapter. The hellscape of the Hadean had not ended, merely evolved. Earth remained a hostile world of intense volcanism, high temperatures, toxic atmosphere, and potentially violent tectonic activity. But the era of planet-sterilizing impacts and global magma oceans had passed. The stage was set for an eon equally extreme but for different reasons. The Archean, when life would emerge and begin the slow process of transforming a poison gas planet into something capable of supporting complex organisms, though that transformation would require 2.5 billion years of patience. The Archean eon opened 4 billion years ago with a planet that had survived its worst traumas, but remained profoundly hostile to anything resembling modern life. This period, stretching across 1.5 billion years until 2.5 billion years ago, witnessed transformations as dramatic as the Hadean's violence, though the mechanisms differed entirely. Where the Hadean had been characterized by bombardment and magma, the Archean would be defined by chemistry, specifically the chemistry of an atmosphere and ocean system completely alien to our experience. The air that would eventually sustain dinosaurs, mammals, and humans did not exist. In its place hung a toxic mixture that would kill any oxygen-breathing organism within seconds. The composition of the Archean atmosphere has been reconstructed through multiple lines of evidence, and the picture that emerges contradicts older assumptions. For decades, many scientists believe the early atmosphere consisted primarily of methane and ammonia, based on experiments in the 1950s that successfully synthesized organic compounds from such mixtures when exposed to electrical sparks simulating lightning. However, more recent geochemical analysis of ancient rocks and theoretical modeling of mantle chemistry has forced a revision. Earth's mantle was probably oxidized relatively early during accretion, meaning volcanic outgassing, the primary source of atmospheric gases, would have produced carbon dioxide and nitrogen as the dominant components, not methane and ammonia. The atmosphere still qualified as reducing compared to today's oxygen-rich air, but it was less reducing than once thought. Carbon dioxide concentrations in the early Archean may have reached several tenths of a bar, meaning atmospheric pressure from carbon dioxide alone equaled 30 to 40% of Earth's entire current atmospheric pressure. Some models suggest even higher values during the Hadean-Archean transition. This massive greenhouse gas abundance served a critical function, warming the planet despite the faint young sunday. The sun's luminosity 4 billion years ago stood at roughly 70% of its current output. Yet geological evidence indicates liquid water persisted on Earth's surface throughout the Archean. Without substantial greenhouse warming, the planet should have frozen solid. Carbon dioxide, along with possible contributions from methane and water vapor, trapped enough heat to maintain temperatures compatible with liquid oceans. This carbon dioxide gradually declined over hundreds of millions of years as the carbonate-silicate cycle sequestered carbon into rocks, but remained abundant enough to prevent freezing. Nitrogen likely constituted the other major atmospheric component, just as it does today, though determining precise concentrations from rocks billions of years old presents enormous challenges. By approximately 3.4 billion years ago, nitrogen had become the dominant atmospheric gas by volume. Unlike carbon dioxide, nitrogen is largely inert and doesn't participate readily in chemical reactions at surface temperatures and pressures. It served primarily as a buffer gas, diluting other more reactive components. Volcanic eruptions continuously replenished nitrogen through outgassing, while some was lost to space through atmospheric escape and some became incorporated into rocks through weathering processes. The balance maintained a substantial nitrogen presence throughout the Archean. Oxygen remained virtually absent. This single fact fundamentally shaped the entire character of Archean Earth. Photodissociation of water vapor by ultraviolet radiation could split molecules into hydrogen and oxygen, but the hydrogen escaped to space while the oxygen quickly reacted with reduced substances. Dissolved iron in the oceans, volcanic gases like hydrogen and hydrogen sulfide, and rocks containing iron-rich minerals. Any oxygen produced was immediately consumed. The atmosphere contained at most trace amounts, perhaps 100,000th to 1 millionth of current levels, effectively zero from a practical standpoint. This had cascading consequences. Without oxygen, no ozone layer formed. Ozone, consisting of 3 oxygen atoms bound together, absorbs dangerous ultraviolet radiation in Earth's upper atmosphere today, protecting surface life from DNA-damaging UV rays. Archean Earth offered no such protection. Ultraviolet radiation struck the surface and shallow waters with full solar intensity. Methane did exist in the Archean atmosphere, though its abundance and timing remained subjects of active research. On prebiotic Earth before life emerged, methane concentrations may have reached only tens of parts per million, produced through geochemical processes like serpentinization, a reaction between water and iron-rich rocks that generates methane and hydrogen. Once methanogenic microorganisms evolved, which likely occurred relatively early in the Archean based on genetic evidence and isotopic signatures in ancient rocks, methane production increased substantially. Methanogens are microbes that produce methane as a metabolic byproduct, typically in oxygen-free environments. They would have thrived in the anoxic Archean oceans and sediments. Their activity could have boosted atmospheric methane to hundreds of parts per million, or possibly higher. Methane is a potent greenhouse gas, roughly 30 times more effective at trapping heat than carbon dioxide over a century-long timescale, so even modest concentrations contributed significantly to planetary warming. Other trace gases added complexity to the atmospheric chemistry. Hydrogen occurred in small but meaningful amounts, produced by volcanic outgassing and possibly by geological reactions with iron-rich rocks. Some researchers have suggested that before methanogenic life evolved, hydrogen might have provided additional greenhouse warming through collision-induced absorption in combination with nitrogen or carbon dioxide. Carbon monoxide, highly reactive and energetically favorable for driving certain chemical reactions, existed as a trace component. Large asteroid impacts could temporarily spike carbon monoxide concentrations to much higher levels by vaporizing carbon-rich crustal material, potentially creating brief windows of unusual atmospheric chemistry. Sulfur compounds, particularly sulfur dioxide and hydrogen sulfide, emerge from volcanic vents, contributing to atmospheric haze and participating in complex photochemical reactions. The oceans of the Archean differed as dramatically from modern seas as the atmosphere differed from modern air. Temperature estimates vary widely depending on methodology, but most researchers agree the oceans were warmer than today, potentially averaging 35 to 55 degrees Celsius or even higher during the earliest Archean. Some isotopic studies of ancient chert, silica-rich sedimentary rock have suggested temperatures as high as 70 degrees Celsius, though debate continues about whether these values reflect actual ocean temperatures or later alteration of the rocks. Regardless of the exact numbers, the trend is clear. Archean oceans were hot, especially compared to today's average surface ocean temperature of approximately 17 degrees Celsius. The chemistry of these hot seas bore no resemblance to the saltwater familiar to anyone who has visited a beach. Modern oceans are oxidized, with dissolved oxygen supporting diverse aerobic life from bacteria to blue whales. Archean oceans contained virtually no dissolved oxygen. Instead, they were rich in dissolved ferrous iron, the reduced form of iron that remains soluble in water. Rivers weathering basaltic rocks on land transported iron to the sea, and massive hydrothermal vent systems on the seafloor continuously pumped iron-rich fluids into the deep ocean. With no oxygen to react with and precipitate this iron as rust, concentrations built to levels thousands of times higher than modern oceans. The water would have appeared greenish or murky from the dissolved metals. This condition, known as a ferruginous ocean, persisted throughout much of the Archean. Silica concentrations also exceeded modern levels dramatically. Today's oceans contain relatively little dissolved silica, because organisms like diatoms and radiolarians extract it to build their shells, constantly depleting the supply. The Archean lacked such organisms. Hydrothermal vents and weathering of silicate rocks supplied silica that accumulated in seawater until it reached saturation and began precipitating chemically as chert. This explains the abundance of chert deposits in Archean rock formations. The silica simply fell out of solution like snowflakes forming in supersaturated air. Some of this precipitation may have been aided by early microbial life, though debates continue about whether Archean chert formation was primarily biological or abiological. Into this alien chemical environment, life emerged. The exact timing remains uncertain and probably always will, since the oldest rocks have been heavily metamorphosed, obscuring or destroying potential biosignatures. The earliest claimed evidence comes from graphite pure carbon, found in metasedimentary rocks from Isua in southwestern Greenland, dated to 3.7 billion years ago. The graphite shows a carbon isotope ratio, suggesting biological origin. Living organisms preferentially incorporate the lighter isotope carbon-12 over carbon-13 during metabolism, leaving a characteristic depletion of carbon-13 in organic material. The Isua graphite displays this depletion, though some scientists argue that non-biological processes can produce similar isotopic patterns, making the evidence suggestive but not definitive. More convincing evidence appears at 3.48 billion years ago, in the Dresser Formation of the Pilbara region in Western Australia. They are stromatolites, layered structures built by microbial mats, occur in ancient hot spring deposits. Stromatolites form when communities of microorganisms, typically cyanobacteria or other photosynthetic bacteria, trap and bind sediment, particles or precipitate minerals as they grow, creating distinctive dome-shaped or columnar layers. The Dresser Formation stromatolites show internal structures consistent with biological construction, fine laminations, specific geometric patterns, and associated organic carbon. While some researchers have questioned whether all Archean stromatolites definitively indicate life, the Dresser specimens are widely accepted as genuine biosignatures, making them among the oldest confirmed fossils on Earth. Additional evidence for 3.47 billion-year-old life comes from barite, a barium sulfate mineral, in the Warrawoona group, also in Western Australia. The sulfur isotopes in this barite show fractionation of up to 21.1% between sulfur-32 and sulfur-34. This degree of fractionation is characteristic of sulfate-reducing bacteria, microorganisms that metabolize sulfate and preferentially process the lighter sulfur-32 isotope. The isotopic signature provides strong evidence that microbial sulfur cycling was already operating by the mid-Archean. Combined with the stromatolite evidence, a picture emerges of diverse microbial life existing by at least 3.5 billion years ago, and possibly earlier. What kinds of organisms populated these early oceans? They were all single-celled microbes, but not necessarily simple. The deepest branches of the tree of life, determined through genetic analysis, include hyperthermophiles, heat-loving organisms that thrive at temperatures above 80 degrees Celsius. Many of these are methanogens or other anaerobes that don't require oxygen. This genetic evidence suggests that early life evolved in hot environments, possibly near hydrothermal vents on the seafloor, where volcanic heat provided energy and chemical gradients drove metabolic reactions. These environments would have been shielded from the intense ultraviolet radiation bathing the surface, solving a major problem for early life lacking DNA repair mechanisms sophisticated enough to cope with UV damage. Photosynthesis evolved relatively early, though pinpointing exactly when remains challenging. The stromatolites from 3.48 billion years ago likely involved phototrophic bacteria, organisms that harvest light energy, though whether they performed oxygenic photosynthesis like modern cyanobacteria or anoxygenic photosynthesis like purple and green sulfur bacteria remains unclear. Anoxygenic photosynthesis uses hydrogen sulfide or ferrous iron as an electron donor instead of water and produces no oxygen. This would have been more suitable for the early Archean environment. Oxygenic photosynthesis, which splits water molecules and releases oxygen, is biochemically more complex and may have evolved later, possibly by 3 billion years ago, though oxygen didn't accumulate in the atmosphere until much later, an event that will be explored in the next chapter. The solid geology of the Archean underwent transformations as significant as the atmospheric and oceanic changes. Continental crust formation accelerated dramatically compared to the Hadean. By 3.5 billion years ago, identifiable cratons, stable continental cores, had formed in what would become Western Australia, Southern Africa, and other regions. These ancient continental fragments, called Archean shields, still exist today, though they've been metamorphosed and deformed by billions of years of geological activity. The continental crust that formed during the Archean differs compositionally from modern continents, reflecting the hotter mantle conditions and more vigorous tectonic processes of the time. Greenstone belts represent some of the most distinctive Archean geological structures. These elongated zones of metamorphosed volcanic and sedimentary rocks formed primarily through submarine volcanism and later tectonic deformation. Typically, they consist of three main layers: lower komatiite lavas rich in magnesium, middle basaltic lava flows, and upper sedimentary rocks including chert and clastic sediments. Komateites, named after the Komati River in South Africa where they were first identified, are ultramafic volcanic rocks that erupted at extremely high temperatures between 1400 and 1600 degrees Celsius, far hotter than modern basaltic lavas. Such temperatures require a much hotter mantle than exists today. which is why komatiites are essentially absent from rocks younger than 2.5 billion years. The formation mechanisms of greenstone belts remain debated, but most models involve volcanic island arcs or oceanic plateaus that form in ancient seas and were later compressed, folded, and incorporated into growing continental masses through accretion. Some greenstone belts show evidence of having formed in rift environments where continental crust was being pulled apart. The preservation of these structures provides critical windows into Archean tectonics and volcanism. Famous greenstone belts include the Barberton Greenstone Belt in South Africa and the Pilbara-Cratton Greenstone Belts in Australia, both dated to approximately 3.5 billion years ago, and both containing some of Earth's oldest confirmed fossils. Banded iron formations, abbreviated as BIFs, constitute another signature Archean rock type with profound implications for understanding ocean chemistry and the eventual rise of oxygen. These sedimentary rocks consist of alternating thin layers, typically millimeters to centimeters thick, of iron-rich minerals like magnetite or hematite and silica-rich chert. The banding creates distinctive striped patterns visible in outcrop and in hand samples. BIFs formed primarily during two major periods, the Archean to early Proterozoic, from roughly 3.8 to 1.8 billion years ago, and a brief resurgence around 700 million years ago. The Archean Proterozoic BIFs represent by far the largest iron deposits on Earth and have been mined extensively for steel production. The formation of banded iron formations required specific conditions that existed in Archean oceans but not in modern seas. Iron-rich fluids from hydrothermal vents and weathering of basaltic rocks dissolved into anoxic seawater, where ferrous iron remained stable. This created oceans saturated with dissolved iron. When cyanobacteria and other photosynthetic organisms began producing oxygen, even before atmospheric oxygen rose appreciably, the oxygen diffused into shallow coastal waters. There, it encountered the dissolved iron and oxidized it, causing ferric iron oxide to precipitate and sink to the seafloor. The alternating bands likely reflect seasonal or cyclic variations in oxygen production, changes in ocean circulation delivering iron to coastal regions, or periodic upwelling of iron-rich deep water. The existence of banded iron formations throughout the late Archean and early Proterozoic demonstrates a critical point. Photosynthetic organisms were producing oxygen for hundreds of millions of years before that oxygen accumulated in the atmosphere. The iron dissolved in the oceans acted as an enormous oxygen sink. Every oxygen molecule produced by photosynthesis immediately reacted with dissolved iron and precipitated as iron oxide. Only after this massive iron reserve had been exhausted, a process requiring hundreds of millions of years, could free oxygen begin accumulating in seawater and eventually bubble into the atmosphere. This delay between the evolution of oxygenic photosynthesis and the oxygenation of the atmosphere is one of Earth history's most important biogeochemical transitions. By the late Archean, around 2.7 billion years ago, microbial life had diversified into numerous metabolic strategies. Methanogens produced methane from carbon dioxide and hydrogen. Sulfate-reducing bacteria metabolized sulfate compounds. Anoxygenic photosynthetic bacteria harvested light energy using hydrogen sulfide or iron as electron donors. And crucially, cyanobacteria had evolved oxygenic photosynthesis, using water as an electron donor and releasing oxygen as a waste product. These organisms formed extensive microbial mats in shallow coastal environments, building the stromatolite structures that became increasingly common in the fossil record. The biochemical machinery required for these diverse metabolic pathways was already sophisticated, suggesting that the origin of life occurred much earlier, possibly in the earliest Archean or even the late Hadean. Continental growth continued through the later Archean through processes that partially resembled modern plate tectonics but operated at different scales and intensities. The hotter mantle produced more oceanic crust, which meant more island arcs and volcanic activity. These volcanic terrains collided and accreted onto the margins of existing continental nuclei, gradually building larger landmasses. By 2.5 billion years ago, cratons had assembled in multiple locations, though they remained separated by vast oceans. The total volume of continental crust by the end of the Archean may have reached 60 to 70% of the present-day continental volume, meaning most of Earth's landmass had formed by this point, though it was distributed differently across the globe. The end of the Archean Eon at 2.5 billion years ago marks not a sudden catastrophe, but rather a gradual transition in Earth's dominant geochemical regime. The stage was set for the most dramatic atmospheric transformation in planetary history, the Great Oxidation Event. Oxygen-producing cyanobacteria had been pumping oxygen into the oceans for hundreds of millions of years, but that oxygen had been consumed by reactions with iron and other reduced substances. Once these sinks became saturated, oxygen would finally accumulate freely. The consequences would be catastrophic for most existing life forms, which had evolved in anoxic conditions and found oxygen toxic. Yet, this catastrophe would also open evolutionary possibilities that had been impossible in the Archean world. Complex life, multicellular organisms, and eventually animals all required oxygen. The poison dawn of the Archean was about to give way to an even more dramatic chemical revolution, one that would make dinosaurs possible billions of years in the future. For nearly 2 billion years, Earth's atmosphere had remained in a stable chemical state, oxygen-free, carbon dioxide-rich, and fundamentally toxic to any organism that relied on aerobic respiration. Microbial life had adapted exquisitely to these conditions, thriving in the anoxic oceans and developing metabolic pathways that extracted energy from reduced chemical compounds. Then, around 2.4 billion years ago, this ancient equilibrium shattered. Oxygen began accumulating in the atmosphere at levels unprecedented in Earth's history, rising from less than 1 part per million to possibly 1 to 10% of present atmospheric levels within a few hundred million years. This transition, known as the Great Oxidation Event or the Oxygen Catastrophe, ranks among the most dramatic biogeochemical upheavals the planet has ever experienced. It poisoned countless species, triggered a potential global glaciation, and fundamentally rewrote the rules governing what kinds of life could exist. The architects of this revolution were cyanobacteria, photosynthetic microorganisms that had evolved oxygenic photosynthesis hundreds of millions of years earlier during the Archean. These organisms perform a chemical reaction that would shape Earth's destiny. They split water molecules using energy from sunlight, extracting electrons to build organic compounds and releasing molecular oxygen as waste. The biochemistry involved extraordinary sophistication. Oxygenic photosynthesis requires two linked photosystems working in sequence, along with specialized proteins capable of catalyzing the energetically difficult splitting of water-strong chemical bonds. This complexity suggests a long evolutionary history, and genetic evidence supports an origin deep in the Archean, possibly as early as 3 billion years ago or even earlier. Yet if cyanobacteria had been producing oxygen for hundreds of millions of years before the Great Oxidation Event, why did oxygen suddenly accumulate around 2.4 billion years ago? The answer lies in oxygen sinks, chemical substances that react with and remove free oxygen from the environment. Throughout the late Archean, every oxygen molecule released by photosynthesis encountered a vast reservoir of reduced materials eager to react with it. Dissolved ferrous iron filled the oceans at concentrations thousands of times higher than modern seawater. When oxygen met this iron, chemical reactions oxidized the ferrous iron to ferric iron, which immediately precipitated as iron oxide minerals and sank to the seafloor, forming the banded iron formations that characterize late Archean and early Proterozoic geology. This process consumed oxygen as fast as cyanobacteria could produce it. On land and in the atmosphere, reduced volcanic gases provided additional oxygen sinks. Hydrogen, methane, and hydrogen sulfide emerging from volcanic vents all reacted readily with oxygen, removing it from the air. The crust itself contained iron-bearing minerals in their reduced state, which oxidized when exposed to weathering. Essentially, Earth's entire surface system, oceans, crust, and atmosphere, existed in a reduced state that had been maintained since the planet's formation. The cumulative capacity of these sinks to absorb oxygen was enormous, far exceeding the oxygen production capacity of early photosynthetic life. For hundreds of millions of years, Oxygen produced in shallow coastal waters where cyanobacteria thrived simply never made it into the open atmosphere in significant quantities. Several factors converged around 2.4 billion years ago to tip this balance. First, the continuous burial of organic carbon over hundreds of millions of years slowly built up a reservoir of reduced carbon locked away in sedimentary rocks. Each time photosynthetic organisms fixed carbon dioxide into organic matter, and that organic matter became buried before decomposing, the oxygen that had been produced during photosynthesis remained in the system rather than being consumed by respiration or decomposition. This represented a net addition of oxygen to the surface environment. Second, changes in the oxidation state of volcanic gases may have occurred. As Earth's mantle continued cooling and evolving chemically, the composition of volcanic emissions may have shifted toward less reducing mixtures, decreasing the atmospheric oxygen sink. Third, and perhaps most importantly, the ocean's dissolved iron reservoir was finally becoming exhausted. After hundreds of millions of years of cyanobacterial oxygen production precipitating iron oxides, the supply of easily accessible dissolved iron had declined substantially. Evidence for this comes from the banded iron formations themselves, which become less common after about 2.5 billion years ago, with a major pulse of deposition ending around 1.8 billion years ago. Once this enormous iron sink had been largely depleted, oxygen produced by photosynthesis could no longer be immediately consumed by reacting with dissolved metals. Instead, it began accumulating in seawater and eventually saturating the surface ocean, allowing oxygen to escape into the atmosphere for the first time in Earth's history. The geological evidence for the Great Oxidation Event comes from multiple independent sources, creating a robust picture of the transition. Perhaps the most compelling evidence involves sulfur isotopes preserved in sedimentary rocks. Sulfur exists in 4 stable isotopes: sulfur-32, sulfur-33, sulfur-34, and sulfur-36. In modern Earth's atmosphere, which contains abundant oxygen and an ozone layer, ultraviolet radiation produces a specific pattern called mass-dependent fractionation in sulfur isotopes. However, in an anoxic atmosphere lacking an ozone shield, intense UV radiation reaching the surface produces different photochemical reactions that create mass-independent fractionation, anomalous ratios between sulfur-33 and sulfur-32 that don't follow normal chemical rules. Sedimentary rocks, older than 2.45 billion years, consistently show mass-independent sulfur isotope fractionation, indicating an oxygen-free atmosphere that allowed UV radiation to penetrate to the surface. Rocks younger than 2.32 billion years show only mass-dependent fractionation, indicating the atmosphere contained enough oxygen to form an ozone layer that blocked UV radiation. The transition between these two states occurred between approximately 2.45 and 2.32 billion years ago, defining the timing of the Great Oxidation Event. The sulfur isotope evidence is particularly powerful because it's difficult to explain through any mechanism other than atmospheric oxygen levels, making it one of geology's clearest signatures of environmental change. Additional geological markers confirm the rise of atmospheric oxygen during the early Proterozoic. Red beds, sedimentary rocks colored by oxidized iron minerals like hematite, appear in the geological record starting around 2.3 to 2 billion years ago and become increasingly common afterward. These distinctive rust-colored formations could only form in the presence of atmospheric oxygen, which oxidized iron during weathering and transport before the sediments were deposited. Archean sediments lack red beds almost entirely, reflecting the absence of oxidizing conditions. The appearance and proliferation of red beds after the Great Oxidation Event provides direct visual evidence of Earth's atmospheric transformation, visible to geologists studying ancient rock outcrops worldwide. The consequences of atmospheric oxygenation were profound and multifaceted. For the anaerobic organisms that had dominated Earth's biosphere for nearly 2 billion years, oxygen represented a deadly poison. Molecular oxygen is highly reactive and damages biological molecules through oxidation. It generates reactive oxygen species, molecules like superoxide and hydrogen peroxide, that attack proteins, lipids, and especially nucleic acids like DNA and RNA. Modern aerobic organisms have evolved elaborate enzymatic defense systems to neutralize these toxic compounds, including catalase and superoxide dismutase. Archean and early Proterozoic anaerobes lacked these defenses entirely, having never encountered significant oxygen concentrations. When oxygen levels rose in their environments, many lineages would have suffered catastrophic cellular damage and died. Isotope geochemistry data from sulfate minerals have been interpreted to indicate a decrease in the size of the biosphere of more than 80% associated with changes in nutrient supplies at the end of the Great Oxidation Event. While this extinction doesn't appear in conventional lists of major mass extinctions, which focus on the Phanerozoic Eon when complex multicellular life existed, it likely ranks as one of the most devastating die-offs in Earth's history, measured by the proportion of biomass eliminated. The oxidative environmental change, compounded by global glaciation, devastated microbial mats that had covered vast areas of Earth's shallow coastal environments and seafloors. Only organisms that could either tolerate oxygen, sequester themselves in anoxic refugia, or adapt through acquiring oxygen-detoxifying biochemistry survived this transition. Yet oxygen also created unprecedented opportunities. Aerobic respiration, using oxygen to burn organic molecules for energy, yields approximately 15 times more energy per glucose molecule than anaerobic fermentation. This enormous energetic advantage meant that organisms capable of using oxygen could support more complex metabolic processes, larger cell sizes, and eventually multicellular body plants. The evolution of mitochondria, the energy-producing organelles in eukaryotic cells, occurred after the Great Oxidation Event through endosymbiosis, one bacterium engulfing another and establishing a permanent partnership. The engulfed bacterium, an aerobic proteobacterium capable of using oxygen, became the mitochondrion, providing its eukaryotic host with vastly enhanced energy production. This event proved critical for the later evolution of complex multicellular life. The Great Oxidation Event also triggered dramatic climate consequences through its impact on atmospheric greenhouse gases. Methane produced by methanogenic archaea throughout the Archean and early Proterozoic had accumulated to concentrations possibly reaching several hundred to several thousand parts per million, far higher than the approximately 1.8 parts per million in today's atmosphere. Methane is a powerful greenhouse gas, and at these concentrations it contributed substantially to keeping Earth warm despite the faint young sunday. However, methane reacts readily with oxygen, oxidizing to form carbon dioxide and water. As atmospheric oxygen levels rose, this reaction proceeded vigorously, consuming vast amounts of methane and replacing it with carbon dioxide, a much weaker greenhouse gas on a molecule-per-molecule basis. The removal of methane's intense greenhouse effect, combined with relatively low carbon dioxide levels, which have been declining throughout the late Archean as the carbonate-silicate cycle sequestered carbon, led to dramatic global cooling. Between approximately 2.45 and 2.22 billion years ago, Earth experienced a series of severe ice ages known collectively as the Huronian glaciation, named after rock formations north of Lake Huron in Ontario, Canada. Glacial deposits from this period, including diamictites, poorly sorted rock containing fragments ranging from clay to boulders, characteristic of glacial till, occur on multiple continents. Evidence suggests ice sheets advanced to low latitudes, possibly reaching the equator, creating conditions resembling or approaching a global snowball Earth state where ice covered most or all of the planet's surface. The Huronian glaciation comprised at least 3 distinct glacial episodes separated by warmer intervals, indicating oscillating climate conditions rather than a single prolonged freeze. The Ramsey Lake, Bruce, and Gauganda formations in the Huronian supergroup each contain glacial diamictites representing separate ice ages. Climate modeling suggests these oscillations may have resulted from feedback mechanisms between oxygen production, methane consumption, atmospheric composition, and temperature. When glaciation reduced biological productivity by covering photosynthetic habitats with ice, oxygen production declined while volcanic outgassing continued adding carbon dioxide and potentially methane to the atmosphere. Eventually, greenhouse warming recovered enough to melt the ice, allowing life to proliferate again and oxygen production to resume, potentially triggering another glacial cycle. The most significant biological innovation following the Great Oxidation Event was the evolution of eukaryotic cells. Eukaryotes, organisms whose cells contain membrane-bound nuclei and complex internal structures called organelles, represent one of life's three domains, alongside bacteria and archaea. All visible multicellular life on Earth, from algae to redwood trees to dinosaurs to humans, consists of eukaryotic cells. The timing of eukaryotic origins remains debated, but most evidence suggests they emerged during the early to middle Proterozoic, likely between 2.1 and 1.6 billion years ago, though some molecular clock estimates suggest earlier origins. Fossils that may represent early eukaryotes appear in rocks approximately 1.8 to 1.6 billion years old. The defining event in eukaryotic evolution was endosymbiosis, the process by which one organism lives inside another in a mutually beneficial relationship. An archaeal host cell engulfed an aerobic bacterium, likely an alpha proteobacterium capable of using oxygen to generate energy through respiration. Rather than being digested, this bacterial cell survived inside its host and established a permanent partnership. Over evolutionary time, the engulfed bacterium transferred most of its genes to the host cell's nucleus and became highly specialized for energy production, transforming into the mitochondrion. All known eukaryotes either possess mitochondria or descended from ancestors that did. Even eukaryotes living in oxygen-free environments today often retain modified mitochondria called hydrogenosomes or mitosomes. This mitochondrial acquisition fundamentally changed what was possible for life. Mitochondria provided eukaryotic cells with vastly more efficient energy production compared to fermentation or other anaerobic metabolic pathways. The approximately 15-fold increase in energy yield from aerobic respiration supported larger cell sizes, more complex internal organization, and eventually multicellularity. The genetic evidence overwhelmingly indicates that mitochondria arose only once in evolution, meaning all eukaryotes share a common ancestor that underwent this crucial endosymbiotic event. The timing of mitochondrial acquisition likely occurred after enough atmospheric oxygen had accumulated to make aerobic respiration advantageous, linking the Great Oxidation Event causally to the evolution of complex life. Following the innovations of the early Proterozoic atmospheric oxygenation, eukaryotic evolution, and mitochondrial endosymbiosis, Earth entered a remarkably stable period that geologists informally call the Boring Billion. Stretching from approximately 1.8 billion to 800 million years ago, this interval showed minimal evidence of major climate changes, tectonic upheavals, or biological innovations. Atmospheric oxygen levels remained low, probably below 10% and possibly below 1% of present levels based on chromium isotope analysis of mid-Proterozoic sedimentary rocks. The oceans were largely anoxic and possibly sulfidic in deep waters, a condition called euxinia where hydrogen sulfide accumulates. These oceans may have appeared murky turquoise or greenish rather than blue. The stability of the Boring Billion may have resulted from negative feedback mechanisms that prevented dramatic environmental change. Continental configurations remained relatively stable, with limited mountain building and subdued plate tectonic activity compared to earlier and later periods. Without major continental collisions and erogenous, weathering rates, which consume atmospheric carbon dioxide, remained low, while volcanic outgassing continued steadily. This balance maintains stable atmospheric carbon dioxide concentrations and consequently stable temperatures. The low nutrient delivery to oceans due to limited continental weathering and erosion kept biological productivity low, preventing oxygen production from rising significantly. The system found an equilibrium that persisted for a billion years. Yet calling this period boring reflects a human timescale bias. During these billion years, eukaryotic life diversified substantially, though the fossil record remained sparse. Sexual reproduction likely evolved, dramatically accelerating the potential for evolutionary innovation by shuffling genes between individuals. The first multicellular eukaryotes appeared, including early algae and possibly early ancestors of fungi. The evolution of various eukaryotic organelles beyond mitochondria, including chloroplasts through a second endosymbiotic event involving a cyanobacterium, occur during this interval. These developments laid essential groundwork for the explosion of complex life that would follow after the Boring Billion ended, even if the pace seemed glacial compared to later evolutionary radiations. The Boring Billion eventually terminated around 800 million years ago, as Earth entered the Neoproterozoic era. Tectonic activity resumed with vigor, supercontinents assembled and fragmented, and most dramatically, oxygen levels began rising again in what's termed the Neoproterozoic oxygenation event. This second oxygenation would drive atmospheric oxygen toward levels approaching modern concentrations, finally crossing the threshold necessary for large, active, multicellular animals. But before that could occur, Earth would endure perhaps its most extreme climate catastrophe yet, a series of glaciations so severe that ice may have encased the entire planet from pole to equator, creating a frozen snowball world that pushed life to the brink of extinction. The oxygen revolution that began 2.4 billion years ago had merely set the stage. The real drama, the emergence of complex multicellular life and the ecosystems that would eventually give rise to animals, still lay ahead, waiting for the frozen planet to thaw. After the relative stability of the Boring Billion, Earth's climate system underwent a catastrophic destabilization that ranks among the most extreme episodes in planetary history. Between approximately 720 and 635 million years ago, during the Cryogenian period of the Neoproterozoic era, the planet experienced at least two major glaciations so severe that ice may have extended from the poles all the way to the equator. Continental glaciers thousands of meters thick covered landmasses, while sea ice potentially encased the entire ocean's surface. Average global temperatures plummeted to perhaps -40 to -50 degrees Celsius. This snowball Earth hypothesis, though debated in its most extreme form, is supported by compelling geological evidence found on every continent, including glacial deposits that formed at tropical latitudes near the ancient equator. The geological evidence for these extreme glaciations comes primarily from distinctive rock formations called diamictites. These poorly sorted sedimentary rocks contain fragments ranging from fine clay particles to massive boulders all mixed together, lacking the size sorting that characterizes rocks deposited by rivers or waves. Diamictites form when glaciers grind across bedrock, incorporating rock fragments of all sizes into the ice, which are then deposited together when the ice melts. The Cryogenian rock record preserves thick diamictite deposits on nearly every ancient continental fragment, from Australia to Africa to North America to South America. What makes these deposits remarkable is their paleolatitude, the latitude at which they formed, determined through paleomagnetic analysis. Paleomagnetic studies measure the orientation of iron-bearing minerals in ancient rocks, which aligned with Earth's magnetic field when the rocks formed. By analyzing this magnetic signature, geologists can determine where on Earth the rock was positioned relative to the magnetic poles when it solidified. Cryogenian diamictites from multiple continents show paleomagnetic signatures indicating formation at latitudes within 10 to 15 degrees of the equator, regions that should have been tropical, even accounting for the dimmer sun of that era. Glacial ice at the equator requires extraordinary circumstances. On modern Earth, even during the most severe ice ages of the past 2 million years, when ice sheets covered Canada and Scandinavia, the tropics remained ice-free, with temperatures supporting rainforests. Cryogenian glaciation operated on an entirely different scale. The Sturtian glaciation, named after rock formations in South Australia, began approximately 717 million years ago and lasted perhaps 50 to 60 million years, though dating remains uncertain. This glaciation left diamictite deposits up to 1,000 meters thick in some regions, indicating sustained ice coverage over millions of years with massive glaciers flowing across continents. The ice sheet scraped and polished underlying bedrock, leaving striations, parallel scratches, that record the direction of ice flow. These striations appear in rocks that formed at tropical latitudes, providing direct physical evidence that glaciers existed in regions that today experience year-round warmth. The extent of ice coverage during the Sturtian remains debated, with some models suggesting complete ice coverage and others proposing that thin ice or patches of open water existed near the equator. Following a period of climate recovery, a second major glaciation struck approximately 650 million years ago. The Marinoan glaciation, named after formations in South Australia's Merino district, may have been even more severe than the Sturtian. This glaciation lasted perhaps 15 million years and produced equally widespread diamictite deposits at low latitudes. Climate models simulating Marinoan conditions suggest that once ice coverage reached approximately 30% of Earth's surface, roughly covering the area that modern ice already covers today, plus the continents at higher latitudes, a runaway ice albedo feedback became inevitable. Ice reflects sunlight far more effectively than dark ocean water or vegetated land, cooling the planet further and allowing ice to expand toward the equator. Once ice reached tropical latitudes, the enhanced reflectivity made the frozen state stable, preventing the planet from warming even during summer. What triggered these catastrophic glaciations remains one of geology's most intriguing questions. The leading hypothesis involves the configuration and weathering of continents during the Neoproterozoic. Paleogeographic reconstruction suggests that large landmasses were positioned at tropical latitudes during this period. When continents sit in the tropics, they experience intense weathering from high temperatures and abundant rainfall. The chemical weathering of silicate rocks consumes carbon dioxide from the atmosphere through reactions that ultimately transport dissolved carbon to the oceans, where it precipitates as carbonate minerals and becomes locked in sediments. If weathering rates exceeded the rate at which volcanic activity replenished atmospheric carbon dioxide, concentrations would have declined progressively. Carbon dioxide is a crucial greenhouse gas, so its removal would have cooled the planet systematically over millions of years. Tectonic activity may have accelerated this carbon dioxide drawdown. The breakup of the supercontinent Rodinia, which had assembled during the Middle Proterozoic, was underway during the Neoproterozoic. Continental rifting creates extensive new rock surfaces exposed to weathering and often produces mountain ranges that enhance weathering rates through increased topographic relief and rainfall. Additionally, rifting may have brought fresh basaltic rock into tropical climates where weathering proceeds most vigorously. Some researchers have suggested that the eruption of large igneous provinces, massive volcanic events that can deposit millions of cubic kilometers of basalt across continental surfaces, provided enormous quantities of highly weatherable rock that consumed atmospheric carbon dioxide through chemical weathering faster than volcanism could replace it. A biological contribution may have amplified the cooling. By the Neoproterozoic, photosynthetic organisms, including algae, had colonized shallow marine environments extensively. Some researchers have proposed that these organisms enhanced weathering by secreting organic acids that dissolve rock minerals, accelerating carbon dioxide consumption. Additionally, the burial of organic carbon produced through photosynthesis represents a net removal of carbon dioxide from the atmosphere-ocean system. If biological productivity increased during the Neoproterozoic, possibly due to rising oxygen levels creating more favorable conditions for eukaryotic algae, the enhanced carbon burial could have contributed to atmospheric carbon dioxide depletion and consequent cooling. The interplay between tectonic, weathering, and biological processes likely created conditions where the climate system became vulnerable to catastrophic glaciation. Once initiated, snowball Earth glaciations proved remarkably difficult to reverse due to the ice albedo feedback effect. With most or all of the ocean surface frozen and continents buried under ice sheets, Earth's surface reflected approximately 60 to 70% of incoming solar radiation back into space, compared to roughly 30% today. This high albedo kept temperatures far below freezing even during summer at the equator. Climate models indicate that once established, a snowball state can persist indefinitely under normal conditions because the planet radiates heat to space more effectively when frozen than it can absorb energy from the sun breaking free from this frozen trap. Required an extraordinary accumulation of greenhouse gases, specifically carbon dioxide, to force the climate past a warming threshold where melting could begin. Volcanic activity provided the escape mechanism. Even during complete glaciation, volcanism continued along mid-ocean ridges at subduction zones and at hotspots like modern Hawaii. These volcanic systems released carbon dioxide steadily into the atmosphere. Under normal conditions, This volcanic outgassing is balanced by weathering processes that remove carbon dioxide from the atmosphere. However, during snowball Earth, continental weathering essentially stopped. Ice sheets thousands of meters thick covered the land, preventing rainfall from reaching rock surfaces and halting the chemical weathering reactions that consumed carbon dioxide. Similarly, ocean weathering ceased because the seas were covered by ice, preventing the formation of carbonate minerals that normally sequester carbon. With removal pathways shut down but volcanic addition continuing, atmospheric carbon dioxide accumulated inexorably. The timescale for carbon dioxide buildup depended on the rate of volcanic outgassing and the duration of glaciation. Estimates suggest it may have taken 10 to 50 million years for atmospheric carbon dioxide to reach concentrations high enough to overcome the ice albedo feedback and initiate deglaciation. Models indicate that carbon dioxide levels may have climbed to 300 to 350 times pre-industrial concentrations, extraordinarily high compared to current levels of approximately 420 parts per million. At these extreme concentrations, the greenhouse effect finally became powerful enough to raise temperatures above freezing at the equator, even with high albedo from ice coverage. Once melting began at low latitudes, the process accelerated rapidly as exposed dark ocean water absorbed more solar energy, creating a runaway deglaciation that could have melted most ice within perhaps 1,000 to 10,000 years. The rapid transition from frozen to greenhouse conditions is recorded in one of geology's most distinctive rock formations, cap carbonates. These layers of carbonate rock, limestone and dolostone, sit directly on top of glacial diamictites in dozens of locations worldwide, with sharp contacts between the glacial deposits and the carbonates showing minimal erosion or time gap. Cap carbonates typically measure 10 to hundreds of meters thick and display unusual features including crystal fans, tubestone structures, and distinctive geochemical signatures. Their formation required very specific conditions: warm temperatures to promote rapid carbonate precipitation, high atmospheric carbon dioxide creating carbonic acid in seawater that later degassed and precipitated as carbonate, and enormous weathering flux from freshly exposed continents delivering dissolved calcium and magnesium to oceans. The geochemical signatures in cap carbonates reveal extreme environmental conditions during deglaciation. Carbon isotope ratios in these carbonates show large negative excursions, meaning they contain more carbon-12 relative to carbon-13 than typical carbonates. This pattern suggests that the carbon came partly from oxidation of organic matter that had accumulated during the glaciation and partly from extremely high atmospheric carbon dioxide levels. Additionally, some cap carbonates show extremely low sulfur-34 values, indicating unusual sulfur cycling during the post-glacial period. The thickness and global distribution of these deposits indicate that carbonate precipitation occurred at extraordinary rates for tens to hundreds of thousands of years following deglaciation, ultimately sequestering the massive amounts of atmospheric carbon dioxide that had accumulated during the frozen interval. The question of how life survived snowball Earth episodes remains one of the hypothesis's most challenging aspects. If the entire ocean surface froze solid to depths of hundreds of meters, photosynthesis would have ceased in the oceans except possibly in small ice-free refugia or beneath thin ice in equatorial regions where some light could penetrate. On land, any photosynthetic organisms would have been buried under kilometers of ice. The cessation of photosynthesis would have collapsed food chains, potentially causing mass extinction. Yet the fossil record shows that diverse life forms, including various types of algae and other eukaryotes, survived through the cryogeny and glaciations, and even diversified afterward. This apparent paradox requires explanation. Several survival mechanisms have been proposed. First, the ice coverage may not have been absolutely complete even during maximum glaciation. Climate models have explored scenarios where thin ice or ice-free regions persisted near the equator, possibly maintained by geothermal heat from submarine volcanism or by dynamic ocean circulation beneath the ice. If open water or sufficiently thin ice existed in some equatorial locations, photosynthetic organisms could have survived in these refugia and expanded globally once deglaciation began. Even ice several meters thick can transmit some light, potentially enough for adapted photosynthetic organisms to survive, though productivity would have been drastically reduced. Second, organisms may have survived in isolated environments not covered by ice. Hydrothermal vents on the deep seafloor would have continued operating throughout glaciation, providing heat, chemical energy, and liquid water environments where chemosynthetic bacteria could thrive independently of sunlight. These vent communities, similar to those found today in deep oceans, could have sustained small ecosystems throughout the frozen period. When deglaciation occurred, organisms from these refugia could have recolonized the newly ice-free oceans. Additionally, volcanic hotspots creating geothermal areas on continents or in shallow seas may have maintained ice-free or thin ice zones where life persisted. Third, some organisms may have survived in a dormant state. Modern microorganisms can form spores or enter states of suspended animation that allow survival for thousands or even millions of years under extreme conditions. If neoproterozoic organisms possess similar capabilities, they could have survived frozen in ice or sediments and revived once conditions improved. The genetic adaptations required for such extreme dormancy are found widely among modern bacteria and some eukaryotes, suggesting these capabilities may have ancient evolutionary origins. The fossil record's preservation of diverse eukaryotic lineages through the cryogenian indicates that whatever survival mechanisms operated, they were sufficiently effective to prevent complete extinction of complex life. The biological and evolutionary consequences of snowball Earth glaciations may have been profound, though disentangling cause and effect across hundreds of millions of years present significant challenges. Following the final Marinoan deglaciation around 635 million years ago, the fossil record shows a remarkable diversification of eukaryotic life. The Ediacaran period, immediately following the Cryogenian, witnessed the appearance of the first large, complex multicellular organisms, the enigmatic Ediacaran biota. These soft-bodied organisms, some reaching lengths of over a meter, represented an entirely new scale of biological organization. Whether Snowball Earth episodes directly triggered this evolutionary radiation remains debated, but the temporal correlation is striking. Several mechanisms could link glaciation to evolutionary innovation. The extreme environmental stress of near-total freezing would have created intense selection pressure, potentially favoring organisms with more sophisticated cellular machinery, better stress tolerance, and more flexible metabolic capabilities. The population bottlenecks created by glaciation, where most organisms perished and only small populations in refugia survived, could have accelerated evolution through founder effects and genetic drift. When deglaciation occurred, the survivors would have encountered a planet essentially empty of competitors, allowing rapid diversification to fill vacant ecological niches. This pattern of stress-induced bottleneck followed by radiation resembles evolutionary dynamics observed after later mass extinctions. The postglacial environment itself may have been unusually favorable for evolutionary innovation. The massive weathering pulse that followed deglaciation would have delivered enormous quantities of nutrients, especially phosphorus, a key limiting nutrient to the oceans. This nutrient influx would have stimulated biological productivity to levels far exceeding normal conditions, potentially supporting larger and more diverse ecosystems than had existed before glaciation. Additionally, oxygen levels began rising again during the Neoproterozoic in what's called the Neoproterozoic oxygenation event. While the exact timing and relationship to Snowball Earth episodes remain unclear, rising oxygen created new metabolic opportunities and eventually crossed thresholds necessary for large, active multicellular animals. The atmospheric and oceanic chemistry during the Cryogenian and its immediate aftermath differed substantially from both earlier and later periods. Before the glaciations, oxygen levels remained relatively low, perhaps 1 to 10% of present atmospheric levels. The deep oceans likely remained anoxic and possibly sulfidic, with only surface waters containing dissolved oxygen. During glaciation, if ice coverage was extensive, photosynthetic oxygen production would have plummeted, and any oxygen in seawater would have been consumed by chemical reactions with reduced compounds. The oceans might have become entirely anoxic temporarily. Following deglaciation, as photosynthesis resumed under intense sunlight and high carbon dioxide, oxygen production could have spiked dramatically. Evidence suggests that by the end of the Ediacaran period around 541 million years ago, atmospheric oxygen had reached levels approaching 10 to 15% of present concentrations, possibly higher. This represented a crucial threshold for animal evolution. Large active animals require substantial oxygen to support their metabolic demands. Simple diffusion of oxygen through tissues becomes insufficient beyond certain body sizes without circulatory systems and respiratory structures. The rise in oxygen levels during and after cryogenian may have removed a fundamental constraint that had prevented animal evolution throughout the earlier Proterozoic despite the existence of eukaryotic cells for well over 1 billion years. The end of the cryogenian period around 635 million years ago marked Earth's final experience with snowball-scale glaciation. Later ice ages occurred, including significant glaciations during the late Ordovician, Carboniferous Permian, and Quaternary periods, but none approached the severity of cryogenian events. Several factors may explain why snowball Earth conditions became less likely in later Earth history. The increasing complexity and extent of the terrestrial biosphere, with plants colonizing land and eventually covering continents with forests, fundamentally altered weathering processes and climate feedbacks. Biological weathering accelerates carbon dioxide consumption, but also creates soil layers that can buffer against runaway weathering. The evolution of shell-forming marine organisms created a massive carbonate buffer system in the oceans that helped stabilize carbon dioxide levels. Additionally, the sun's luminosity has been gradually increasing throughout Earth's history as hydrogen fusion in the solar core changes the sun's internal structure. By the late Neoproterozoic, the sun was already about 6% brighter than during the cryogenian. This increased solar energy input raises the amount of greenhouse gas reduction required to trigger runaway glaciation, making snowball states progressively less likely over time. Combined with biological and geochemical feedbacks, the increasing solar luminosity has made Earth's climate more resistant to extreme glaciation, even as ice ages have continued to occur. The cryogenian period closed with Earth emerging for its final snowball episode into the Ediacaran, a time of relative warmth, high biological productivity, and crucially, rising complexity in the biosphere. The stage was now set for an even more dramatic transformation than anything the Archean, Proterozoic, or Cryogenian had witnessed. Within roughly 40 million years after the end of the Marinoan glaciation, the first true animals would appear in the fossil record. Not microscopic organisms or simple cell colonies, but complex multicellular creatures with specialized tissues, organs, and body plans. The Cambrian Explosion loomed on the horizon, but before that could occur, the Ediacaran biota would populate the seafloor with strange frond-like organisms unlike anything seen before or since. The journey from the Hadean Hellscape through the poison Archean seas, across the oxygen revolution and boring billion, and finally through the frozen nightmare of snowball Earth had required 3.5 billion years. But this was merely the prologue. The world the dinosaurs would eventually inherit was still separated from the cryogenian by more than 400 million years of continued evolution, mass extinctions, continental movements, atmospheric changes, and biological innovations. The truly horrifying creatures, the monsters of the Cambrian seas, the armored nightmares of the Devonian, the giant arthropods of the Carboniferous, and finally the catastrophic Permian extinction that would nearly sterilize the planet, still lay ahead in Earth's tumultuous pre-dinosaurian history. The Ediacaran period, which followed the final snowball Earth glaciation, witnessed the first appearance of large, complex multicellular organisms. These enigmatic creatures, known collectively as the Ediacaran biota, populated the seafloor between approximately 575 and 541 million years ago. Most were soft-bodied organisms with strange geometries, quilted fronds, discs, and ribbed forms that resembled nothing in the modern world. Some researchers have interpreted them as early animals, others as extinct experimental body plans, and still others as giant protists or colonial organisms. They lived in relatively calm, shallow marine environments, often forming dense communities on microbial mats that covered the seafloor. These organisms represented a major step in complexity beyond single-celled life, but they remained sessile or slow-moving, lacking hard parts, predatory lifestyles, and diverse body plans that would characterize the animals to come. Then, beginning approximately 541 million years ago, at the start of the Cambrian period, Earth's oceans underwent a biological revolution of staggering scope and speed. Within a geologically brief interval, perhaps 10 to 25 million years, though some estimates extend it to 40 million years, nearly all major animal body plans appeared in the fossil record. This event, known as the Cambrian Explosion, saw the sudden emergence of arthropods with jointed legs and compound eyes, mollusks with shells, annelid worms with segmented bodies, echinoderms with radial symmetry, and chordates with notochords, the phylum that would eventually give rise to vertebrates including fish, amphibians, reptiles, and ultimately dinosaurs. The speed and comprehensiveness of this diversification have made the Cambrian Explosion one of evolution's most studied and debated episodes. The fossil record prior to the Cambrian consists almost entirely of microscopic organisms, stromatolites, and the soft-bodied ediacaran forms. Hardshell fossils are exceedingly rare in Precambrian rocks. This changed dramatically in the earliest Cambrian, approximately 541 million years ago, when small shelly fossils began appearing in abundance. These millimeter to centimeter sized structures, tubes, cones, plates, and spines made of calcium carbonate or calcium phosphate, represented the mineralized skeletons or protective coverings of various small marine animals. The appearance of these hard parts marks a fundamental transition in how organisms constructed their bodies and interacted with their environment. Biomineralization, the biological production of mineralized structures like shells and skeletons, became widespread rapidly, suggesting that selective pressures favoring protective hard parts had intensified dramatically. The most spectacular window into Cambrian life comes from exceptional fossil deposits called Lagerstätten, where soft tissues are preserved in exquisite detail rather than being lost to decay. The most famous of these is the Burgess Shale in British Columbia, Canada, dated to approximately 508 million years ago in the Middle Cambrian. Discovered in 1909 by paleontologist Charles Doolittle Walcott, the Burgess Shale preserves not just hard shells but also soft body parts, muscles, guts, gills, and eyes, providing unprecedented insight into Cambrian animal anatomy and diversity. The creatures preserved in this deposit were unlike anything living today, combining body plan features in unexpected ways and exhibiting morphologies that seem alien even after more than a century of study. Anomalocaris, whose name means abnormal shrimp, ranks among the Burgess Shale's most spectacular and bizarre inhabitants. This predator reached lengths of up to 1 meter or possibly more, enormous by Cambrian standards, making it one of the largest animals of its time. Its body consisted of a series of overlapping lobes along the sides that propelled it through the water with undulating movements. At the front, 2 large appendages equipped with spines reached forward to grasp prey and bring it to the circular mouth, which was ringed with plates arranged like a pineapple slice. This mouth structure, when first discovered, was initially interpreted as a jellyfish before researchers understood it belonged to Anomalocaris. The creature possessed large compound eyes on stalks, giving it sophisticated vision to hunt in the Cambrian seas. Anomalocaris belonged to a group called radiodonts, which represented some of the ocean's apex predators during the early and Middle Cambrian. Hallucigenia earned its name from its thoroughly bizarre appearance when first reconstructed. This small worm-like creature, typically a few centimeters long, possessed a tubular body with 7 or 8 pairs of legs terminating in claws on one side and 7 or 8 pairs of spines projecting upward on the other side. For years, paleontologists couldn't determine which end was the head and which was the tail, or even which side was up. Early reconstructions placed the animal upside down with tentacles on top. Only after additional specimens were discovered and analyzed did the correct orientation emerge. The creature walked on the legs while the spines protected its back from predators attacking from above. Hallucigenia belonged to a group called Lobopodians, which are thought to be related to modern velvet worms and possibly to the ancestors of arthropods. Its strange anatomy illustrates the experimental nature of early animal evolution when body plans were being tested that have no modern equivalents. Opabinia presented another morphological puzzle that challenged paleontologists' understanding of animal body plans. This creature, about 7 centimeters long, possessed 5 eyes arranged across the top of its head, 2 pairs flanking a central 5th eye. Perhaps most remarkably, it had a long, flexible proboscis extending from the front of its head, tipped with a grasping claw that could reach forward and down to capture prey from the seafloor and deliver it to the mouth located underneath and behind the head. The body bore lateral lobes that provided propulsion through the water. When Opabinia was first presented at a scientific conference, the audience reportedly burst into laughter at its absurd appearance, finding it difficult to believe such a creature had actually existed. Yet multiple well-preserved specimens confirm its reality, forcing recognition that Cambrian animals explored body plan possibilities far beyond the range of modern fauna. Wawaxia represented yet another enigmatic form. This creature, a few centimeters long, crawled across the seafloor covered in protective scales and bearing 2 rows of longer spines projecting upward. Its mouth faced downward and possessed a radula-like feeding structure similar to modern mollusks, suggesting a possible relationship to that phylum, though its overall body plan and scale armor are unlike any living mollusk. The combination of features made classification difficult. It might represent an early mollusk, an early annelid worm, or a member of an extinct group that combined features of multiple phyla. The uncertainty surrounding Wawaxia's relationships highlights how Cambrian animals mixed and matched anatomical features in ways that don't fit neatly into modern taxonomic categories. Marella, sometimes called the lace crab, was actually the most abundant arthropod in the Burgess Shale, with thousands of specimens collected. This creature, typically about 2 centimeters long, possessed a head shield from which extended 2 pairs of curved spines sweeping backward. It had numerous body segments, each bearing a pair of branch appendages used for both walking and respiration. Despite its abundance and excellent preservation, determining Marella's exact relationships within the arthropods proved challenging, because it combined features seen in various modern arthropod groups while lacking the specializations characteristic of any particular lineage. It likely represents an early experimental arthropod design from before the major arthropod groups had fully differentiated. The arthropods, animals with jointed legs, segmented bodies, and external skeletons, underwent explosive diversification during the Cambrian. By the Middle Cambrian, arthropods had already split into multiple major lineages. Trilobites, characterized by their 3-lobe body plan with a central axis and 2 lateral lobes, became incredibly diverse and abundant, with thousands of species evolving by the end of the Cambrian. These animals possessed compound eyes similar to modern insects and crustaceans, segmented bodies with multiple pairs of legs, and hard calcified exoskeletons that made them excellent candidates for fossilization. Trilobite fossils are so abundant in Cambrian rocks that they serve as index fossils for dating and correlating rock layers worldwide. Other major animal phyla appeared alongside the arthropods during the Cambrian Explosion. Mollusks, the group that today includes snails, clams, squid, and octopuses, were present from the earliest Cambrian onward. Early mollusks bore simple cap-shaped or cone-shaped shells and crawled across the seafloor, grazing on microbial mats or filtering particles from the water. Some evolved into more complex forms with coiled shells or protective plates. The diversity of molluscan body plans expanded rapidly, establishing the basic anatomical template: a muscular foot for locomotion, a mantle that secretes the shell, and a radula for feeding that would characterize the phylum for the next 500 million years. Brachiopods, often called lamp shells due to their resemblance to ancient oil lamps, became abundant during the Cambrian and would dominate many marine environments throughout the Paleozoic era. These animals superficially resemble clams, with 2 hinged shells protecting the soft body inside, but their internal anatomy differs fundamentally from mollusks. Brachiopods attach to hard surfaces via a stalk called a pedicle and feed by filtering water through a specialized structure called a lophophore, a horseshoe-shaped organ bearing numerous ciliated tentacles that create currents to capture food particles. Cambrian brachiopods diversified into numerous forms, occupying niches in shallow and deep waters across the world's oceans. Echinoderms, the group including modern starfish, sea urchins, and sea cucumbers, appear during the early Cambrian, though the earliest forms looked nothing like their living descendants. These first echinoderms lacked the perfect five-fold radial symmetry characteristic of modern forms, and instead displayed irregular or asymmetric body plans. Some early echinoderms were asymmetric filter feeders that attached to the seafloor, while others crawled on jointed stems. Over the course of the Cambrian, echinoderms experimented with diverse body architectures before eventually converging on the radial symmetry and water vascular system that define the group today. The evolution of their distinctive calcified endoskeleton, composed of individual plates, made echinoderms excellent candidates for preservation in the fossil record. Perhaps most significantly for the eventual evolution of dinosaurs and humans, the earliest chordates appeared during the Cambrian. Chordates are animals possessing a notochord, a flexible rod running along the back at some point in their development, along with a dorsal nerve cord, pharyngeal slits, and a post-anal tail. Modern chordates include tunicates, lancelets, and vertebrates. The Burgess Shale preserved several early chordate species, the most famous being Pikaia, a small eel-like creature about 5 centimeters long that swam through Cambrian seas using undulating body movements. Pikaia possessed a clear notochord, segmented muscles along its body, and tentacles around its mouth for filter feeding. While not a direct ancestor of vertebrates, Pikaia represents the type of organism from which vertebrates would eventually evolve. An even more primitive chordate relative from the Cambrian was Hakichthyes, discovered in the Chengjiang deposits of China dated to approximately 520 million years ago. This creature, barely 3 centimeters long, shows features that place it very close to the vertebrate lineage. It possessed a skull, a backbone-like structure with primitive vertebrae, and possible cartilaginous fin rays. Hakichthyes and related forms like Miloconmingia represent the earliest known fish-like animals, establishing that vertebrates had diverged from other chordates by at least the early Cambrian. From these humble beginnings would eventually arise the jawed fish, amphibians, reptiles, and dinosaurs that would dominate later eras. The causes of the Cambrian explosion remain actively debated, with researchers proposing multiple contributing factors rather than a single trigger. Rising oxygen levels almost certainly played a crucial role. By the late Ediacaran and early Cambrian, atmospheric oxygen had reached perhaps 10 to 15% of present levels, still well below the modern 21%, but high enough to support active, mobile animals with higher metabolic demands. Oxygen enables aerobic respiration, which generates far more energy per molecule of food than anaerobic metabolism. This energy surplus permitted the evolution of muscles for active movement, nervous systems for coordination, and larger body sizes. Animals with higher oxygen requirements, particularly active predators, could not have existed in the low-oxygen Proterozoic world. The evolution of predation itself may have driven much of the Cambrian diversification through evolutionary arms races between hunters and prey. Evidence of predation appears in the fossil record shortly before and during the Cambrian explosion. Some Ediacaran fossils of Cloudina, small tube-dwelling organisms from approximately 550 million years ago, show holes that may have been drilled by predators attempting to reach the soft tissue inside. Once predation became widespread, prey species faced intense selective pressure to develop protective adaptations. Shells, spines, armor plates, and the ability to burrow into sediments all provided defenses against being eaten. Conversely, predators evolved increasingly sophisticated hunting strategies, sensory systems, and feeding structures to overcome these defenses. This predator-prey coevolution may have accelerated the diversification of body plans and ecological strategies. The evolution of vision represented another potential trigger or accelerator of the Cambrian explosion. Eyes appear suddenly in the fossil record during the early Cambrian. Arthropods like trilobites possessed complex compound eyes virtually identical in structure to those of modern insects and crustaceans. Vision at a distance fundamentally changes the nature of predator-prey interactions. Before eyes evolved, hunting and evading relied on chemical detection, touch, and pressure sensing, all relatively short-range senses. With vision, predators could spot prey from meters away, while prey could see threats approaching and flee. This created strong selective pressure for faster locomotion, better defensive structures, and more sophisticated behaviors. However, some researchers question whether vision alone could have triggered such a dramatic radiation, noting that other senses can also detect threats at a distance underwater. Yet their earlier evolution didn't produce comparable explosions of diversity. Genetic and developmental changes likely enabled the rapid morphological diversification seen in the Cambrian. The evolution of Hox genes, regulatory genes that control body plan development, and the positioning of body parts along the head-to-tail axis occurred before the Cambrian and provided a genetic toolkit for building complex, segmented body plans. Changes in the regulation and expression of these developmental control genes could produce significant morphological innovations rapidly without requiring wholesale rewrites of the genome. The genetic flexibility of early animals before body plans became locked into stable configurations through millions of years of optimization may have allowed morphological experimentation on a scale impossible in later eras when ecological niches were already filled by incumbent species. Environmental factors also contributed to creating favorable conditions for rapid diversification. The continental configuration during the Cambrian provided extensive shallow marine shelves, broad, flat areas of seafloor at depths of tens to hundreds of meters where sunlight penetrated and nutrients were abundant. These shallow seas covered portions of most continents, creating vast expanses of productive habitat. The warm climate, lack of polar ice caps, and high sea levels meant these shallow marine environments were widely distributed, allowing animals to diversify and spread globally. The carbonate chemistry of the oceans had also reached a state where biomineralization, producing shells and skeletons from calcium carbonate or calcium phosphate, became energetically favorable, removing a potential barrier to the evolution of hard parts. By the Middle Cambrian, approximately 508 million years ago, the basic ecological structure of marine ecosystems had been established. The seafloor hosted diverse communities of filter feeders, deposit feeders, scavengers, and prey animals, while active predators patrolled the water column above. Food webs had become complex, with multiple trophic levels and diverse feeding strategies. Burrowing animals excavated networks of tunnels in seafloor sediments, creating three-dimensional habitat complexity that hadn't existed in Ediacaran times when most life lived on flat microbial mats. This bioturbation, the mixing and reworking of sediments by organisms, fundamentally changed seafloor chemistry and ecology, making it difficult for the flat-lying Ediacaran body forms to persist. The Cambrian fauna achieved impressive sizes for their time, though they remained small by later standards. Anomalocaris, reaching lengths of up to 1 meter, was likely the largest animal of the early and Middle Cambrian. Most other animals measured centimeters to tens of centimeters. However, size isn't the most important measure of the Cambrian explosion's significance. What matters is disparity, the range of different body plans and ecological strategies. By the end of the Cambrian, essentially all major animal phyla that would ever exist had appeared. Later evolutionary history would see enormous increases in diversity, the number of species, but not in disparity. No fundamentally new body plans emerged after the Cambrian comparable to the initial appearance of arthropods, mollusks, echinoderms, and chordates. The fossil record's preservation of Cambrian life depend heavily on the exceptional lagerstatin deposits like the Burgess Shale and Chengjiang. Normal fossilization preserves only hard parts, shells, bones, and other mineralized structures. Soft tissues typically decay within days or weeks of death, leaving no trace. The exceptional preservation in lagerstatin occurs when animals are rapidly buried in fine sediment under low oxygen conditions that inhibit bacterial decay. The Burgess Shale animals were apparently buried by underwater mudslides that swept them into deep water, oxygen-poor environments where fine clay particles encased their bodies. Over millions of years, minerals gradually replaced the organic tissues cell by cell, preserving structures like muscles, gills, and eyes in exquisite detail. Without these exceptional deposits, our understanding of Cambrian life will be limited to shelled organisms and would miss most of the soft-bodied diversity. The Cambrian period lasted approximately 54 million years, from 541 to 485 million years ago. The explosion of animal diversity occupied primarily the first 15 to 20 million years, with the Middle and Late Cambrian seeing consolidation and refinement of the body plans that had emerged rather than continued morphological innovation at the same pace. Trilobites diversified extensively through the Middle and Late Cambrian, evolving thousands of species adapted to various ecological niches. Some became tiny deposit feeders, others grew large as predators, and still others developed elaborate spines presumably for defense or display. The success of trilobites in particular illustrates that once a successful body plan emerges, it can spawn enormous diversity through variations on a theme. Two major extinction events punctuated the Cambrian, causing significant turnover in marine communities. The first occurred during the Middle Cambrian, approximately 510 million years ago, when sea levels dropped and shallow marine habitats contracted. This extinction eliminated many archaeocyathids, reef-building sponge-like organisms that had created some of Earth's first complex reef structures. The second major extinction marked the end of the Cambrian approximately 485 million years ago, when changing ocean chemistry and possibly cooling temperatures eliminated many trilobite families and other invertebrate groups. However, neither of these extinctions approached the severity of later catastrophes like the Ordovician or Permian mass extinctions. The Cambrian fauna largely persisted into the Ordovician period, where they continued diversifying and evolving. By the close of the Cambrian, Earth's oceans teemed with animal life of a complexity and diversity unimaginable 500 million years earlier. Every major body plan that would characterize animal life for the remainder of Earth's history had been established. The strange experimental forms like Opabinia and Hallucigenia would go extinct, their unusual body architectures ultimately unsuccessful, but the successful designs, the arthropod plan, the mollusk plan, the echinoderm plan, and crucially the chordate plan, would persist and diversify into the hundreds of thousands of species that would populate Paleozoic seas. Most importantly for the eventual evolution of dinosaurs, the early chordate fish were present, swimming through Cambrian waters, their primitive backbones and skulls already establishing the vertebrate architecture that would be elaborated and refined over the next 300 million years until it produced the first dinosaurs in the Triassic period. The Cambrian explosion had set the stage, but the drama of life before the dinosaurs was far from over. Ahead lay the Ordovician, when marine life would grow to unprecedented sizes, followed by the first tentative invasions of land that would transform barren continents into thriving ecosystems. The journey from Cambrian seas to Triassic dinosaurs still required 300 million years of evolution, extinction, and adaptation. The Ordovician period opened approximately 485 million years ago, inheriting the diverse marine ecosystems established during the Cambrian explosion. Over the next 41 million years, life in Earth's oceans would undergo a second major radiation, often overshadowed by the more famous Cambrian event but equally significant in scale. The Ordovician saw marine biodiversity roughly triple compared to Cambrian levels, with total genus diversity increasing from approximately 500 to 1,500 genera by the Middle Ordovician. This period witnessed the rise of some of the largest invertebrate predators ever to swim the seas, the proliferation of complex reef ecosystems, and crucially, the emergence of the first true vertebrates with jaws and paired fins, the ancestors of all later fish, amphibians, reptiles, and dinosaurs. The Ordovician oceans were warmer and shallower than modern seas, with greenhouse conditions maintaining temperatures well above current averages. Sea levels stood much higher than today, flooding the continental interiors and creating vast shallow epicontinental seas, broad expanses of warm, sunlit water covering what are now dry land areas in North America, Europe, Asia, and other continents. These shallow seas provided ideal habitats for bottom-dwelling invertebrates and created extensive areas where photosynthetic organisms could thrive, supporting productive food webs. The climate lacked polar ice caps, and tropical conditions extended to higher latitudes than in the modern world. Atmospheric carbon dioxide levels remained elevated compared to recent geological periods, maintaining the greenhouse warm through enhanced heat trapping. Continental positions during the Ordovician differed dramatically from today's familiar geography. The supercontinent Gondwana, comprising what would eventually become South America, Africa, Antarctica, Australia, and India, sat centered over the South Pole. However, even this polar position didn't produce ice sheets during most of the Ordovician due to the warm climate. Laurentia, the continental core of modern North America, straddled the equator with its eastern margin facing a tropical ocean called the Iapetus Ocean. Baltica, containing the crustal foundations of modern Scandinavia and Eastern Europe, occupied mid-latitudes in the southern hemisphere. Smaller continental fragments, including Siberia and various Asian terrains, were scattered across the globe. The distribution of these landmasses, with most sitting at low to middle latitudes, contributed to the warm climate by minimizing land area in polar regions where ice sheets could form. Marine invertebrates achieved unprecedented diversity and ecological complexity during the Ordovician. Trilobites, which had diversified extensively during the Cambrian, continued evolving into thousands of species occupying varied ecological niches. Some trilobites became specialized deposit feeders, sifting through seafloor sediments for organic particles. Others developed predatory lifestyles, using modified appendages to capture prey. Still others evolved defensive adaptations including elaborate spines, the ability to roll into protective balls, and even sophisticated compound eyes mounted on stalks that allowed them to see while burrowed in sediment with only the eyes protruding. Ordovician trilobite assemblages showed remarkable diversity, with some fossil localities preserving dozens of species coexisting in the same habitat, each specialized for particular food sources or microhabitats. Brachiopods underwent explosive radiation during the Ordovician, becoming the dominant filter-feeding animals in many marine environments. These lampshell creatures diversified into hundreds of genera, developing varied shell shapes, sizes, and ornamentation patterns. Some grew smooth, streamlined shells for life in current-swept environments, while others developed elaborate ridges, folds, and spines. Giant brachiopods reaching sizes of 10 to 15 centimeters appeared, far larger than most Cambrian forms. Brachiopods attached to hard substrates using muscular stalks or cemented directly to rocks, creating dense populations that carpeted the seafloor in productive shallow waters. Their filtering activity processed enormous volumes of seawater, extracting microscopic food particles and playing crucial roles in nutrient cycling. Bryozoans, colonial animals that superficially resemble corals but belong to a different phylum, experienced their first major diversification during the Ordovician. These organisms consist of tiny individual zooids living in connected chambers, together forming colonies that can reach substantial sizes. Ordovician bryozoan colonies grew in varied forms including branching structures, encrusting sheets, and lacy fenestrated patterns. Some bryozoan colonies contributed to reef construction, while others formed meadow-like thickets on the seafloor. The success of bryozoans added another dimension to marine ecosystems, increasing habitat complexity and providing surfaces for other organisms to settle on or hide among. The Ordovician witnessed the first major reef-building ecosystems since the Cambrian archaeocyanid reefs had collapsed. These Ordovician reefs were constructed primarily by various organisms working in combination. Tabulate and rugose corals, two groups that would dominate reef construction throughout the Paleozoic, appeared and began building substantial structures. Unlike modern scleractinian corals, which host photosynthetic algae in their tissues and thus require shallow sunlit waters, Paleozoic corals relied primarily on filtering food from the water and could occupy a wider range of depths. Stromatoporoid sponges, which secreted layered calcium carbonate skeletons, became major reef builders, sometimes forming massive dome-shaped structures several meters across. These reefs created three-dimensional habitat complexity, providing shelter for countless organisms and increasing overall ecosystem diversity. Echinoderms radiated explosively during the Ordovician, achieving their greatest diversity in the group's entire history. Beyond the familiar starfish, sea urchins, and sea cucumbers that survive today, the Ordovician seas hosted numerous bizarre echinoderm groups now extinct. Crinoids, or sea lilies, became particularly abundant and diverse. These animals consist of a cup-shaped body mounted on a segmented stalk that anchors to the seafloor, with feathery arms extending upward to filter food from the water. Ordovician crinoid forests covered vast areas of seafloor, their stalks swaying in currents while their filtering arms captured passing particles. Some crinoid beds achieved such density that their disarticulated skeletal fragments accumulated in thick deposits that later lithified into limestone composed almost entirely of crinoid columnals, the cylindrical segments that made up their stalks. Other strange echinoderms populated Ordovician seas alongside the crinoids. Cystoids, bearing irregular plated bodies with respiratory pores arranged in geometric patterns, attached to hard surfaces and filtered food from passing currents. Blastoids, with their distinctive bud-shaped bodies and five-fold symmetry, would later become common in the Carboniferous but had their origins in the Ordovician. Edrioasteroids, disc-shaped echinoderms that encrusted shells and hard surfaces, displayed curved feeding grooves spiraling across their upper surfaces. The diversity of body plans among Ordovician echinoderms illustrates the evolutionary experimentation still occurring as animal groups explored morphological possibilities opened up by the Cambrian Explosion. The apex predators of Ordovician seas were nautiloids, cephalopod mollusks related to modern nautilus, squid, and octopus. Ordovician nautiloids achieved sizes that dwarf their modern relatives, with some species producing straight, conical shells reaching lengths of 3 to 4 meters and possibly even larger. The largest known species, including members of the genus Camarasaurus, rank among the largest animals of their time and the largest known shelled cephalopods in Earth's history. These colossal predators swam through Ordovician seas using jet propulsion, expelling water through a muscular funnel to generate thrust while their shells provided buoyancy control through gas-filled chambers. The anatomy of these giant nautiloids reveals sophisticated adaptations for predatory life. The animal lived in the final chamber at the wide end of the shell, with tentacles extending forward to capture prey. Unlike the complex sucker-bearing tentacles of modern squid and octopus, nautiloid tentacles were simpler structures, but numerous, possibly as many as 90 in some species. The mouth bore a powerful beak made of chitin, capable of crushing shells and tearing flesh. Large eyes provided vision for hunting in the relatively well-lit shallow seas where these predators prowled. The posterior portion of the shell contained a series of gas-filled chambers separated by walls called septa, with a tube called a siphuncle running through these chambers to regulate buoyancy by adjusting gas and fluid content. Not all nautiloids bore straight shells. The Ordovicians saw extensive experimentation with shell geometry among cephalopods. Some species developed tightly coiled shells resembling modern nautilus, while others produced loosely coiled forms, and still others created shells that curve into U-shapes or irregular spirals. This morphological diversity suggests different swimming styles, hunting strategies, and habitat preferences. Straight-shelled forms like Camarasaurus likely cruised slowly through open water, using their size and predatory prowess to dominate. Coiled forms may have been more maneuverable, better suited for navigating among reefs and seafloor structures. The success of nautiloids as predators reshaped Ordovician marine ecosystems, creating selective pressure for prey species to develop better defenses and driving evolutionary arms races between hunters and hunted. The first vertebrates with mineralized skeletons appeared during the Ordovician, representing a crucial milestone in the lineage that would eventually produce dinosaurs. The earliest fish-like vertebrates from the Cambrian and early Ordovician, such as the conodonts and various jawless fish, possessed cartilaginous internal skeletons and lacked the hard mineralized bones and scales characteristic of later fish. During the Ordovician, true bony armor appeared in a group called the ostracoderms, primitive jawless fish covered in thick bony plates and scales. These armored fish, typically 10 to 30 centimeters long, live primarily as bottom dwellers, using their sucker-like mouths to feed on organic particles and sediments or to filter food from water. Erandaspis and Sacabambaspes, two of the earliest well-known armored fish, appear in Ordovician rocks from approximately 470 million years ago. These creatures bore heavy bony shields covering their heads and anterior bodies, with the posterior portions covered in overlapping scales. The armor provided protection from predators, particularly the giant nautiloids that hunted Ordovician seas. The weight of this armor meant these early fish were poor swimmers, restricted mainly to bottom-dwelling lifestyles where they were relatively safe from predators cruising in open water above. Despite their limitations, these armored jawless fish represented a major evolutionary advance, They were the first vertebrates to develop the mineralized skeletal tissues that would become characteristic of nearly all later fish, amphibians, reptiles, birds, and mammals. The conodonts, mysterious eel-like vertebrates, typically only a few centimeters long, proliferated during the Ordovician and left an abundant fossil record, though not of their bodies. Conodont animals possess soft bodies that rarely fossilized, but their feeding apparatus, complex arrays of tiny tooth-like structures made of mineralized tissue, preserved readily, and occur in vast numbers in marine sedimentary rocks. For more than a century after their discovery, paleontologists debated what conodonts were, variously interpreting the fossils as parts of worms, mollusks, or other invertebrates. Only when complete conodont body fossils were finally discovered in exceptional preservation sites did researchers recognize them as primitive vertebrates. The conodont elements, which functioned as teeth for grasping and processing prey, represent some of the earliest mineralized structures produced by vertebrates and provide important evolutionary information about early vertebrate feeding adaptations. Graptolites, colonial animals belonging to the hemichordates, a phylum related to echinoderms and chordates, achieved extraordinary abundance and diversity during the Ordovician. These organisms lived in colonies composed of multiple zooids housed in connected tubular structures called thecae, arranged along one or more branches. Most Ordovician graptolites were planktonic, drifting in ocean currents with their colonies suspended by floats or attached to floating organic debris. Graptolite colonies displayed diverse architectures. Some species produced single straight branches, others developed elaborate branching patterns, and still others created net-like or spiral configurations. The variety of forms allowed different species to occupy distinct niches within the planktonic realm. The abundance of graptolites in Ordovician marine environments was extraordinary. When these colonial animals died, their carbonized remains sank to the seafloor and accumulated in sediments. Many black shales from the Ordovician contain such dense concentrations of flattened graptolite fossils that rock surfaces appear covered with silvery organic traces, sometimes preserving multiple species in the same layers. This abundance makes graptolites exceptionally useful as index fossils for dating and correlating Ordovician rock formations. Because different graptolite species evolved rapidly and had wide geographic distributions as planktonic organisms carried by ocean currents, geologists can identify narrow time intervals, sometimes just a few million years, based on which graptolite species occur in a particular rock layer. This biostratigraphic utility has made graptolites invaluable for understanding the detailed chronology of the Ordovician period. The Middle Ordovician, approximately 460 million years ago, marked the peak of marine biodiversity during this period. Genus-level diversity had tripled compared to the Cambrian, and complex multi-tiered ecosystems occupied the extensive shallow seas covering continental margins and interiors. Food webs included multiple trophic levels, photosynthetic microorganisms and algae forming the base, small filter feeders and deposit feeders consuming organic particles, larger invertebrates feeding on these smaller organisms, and finally the giant nautiloid predators at the apex. Dead organic matter supported scavenger communities, while specialized parasites exploited living hosts. The complexity rivaled that of modern marine ecosystems in many respects, though the cast of characters differed dramatically from today's oceans. This flourishing underwater empire came to an abrupt and catastrophic end approximately 444 million years ago, in the late Ordovician mass extinction, one of the 5 largest extinction events in Earth's history. This extinction actually comprised 2 distinct pulses of species loss separated by perhaps 1 million years, occurring during the final stages of the Ordovician and the early Silurian period. The first pulse eliminated approximately 60% of marine genera, while the second pulse claimed another 20% of the survivors. In total, an estimated 85% of marine species perished, making this one of the deadliest events in the fossil record measured by species loss, though the percentage of higher taxonomic groups like families and orders that went extinct was lower than in some other mass extinctions. The cause of this catastrophe was climate change of spectacular severity, specifically rapid global cooling that triggered the growth of massive ice sheets on the supercontinent Gondwana, which sat over the South Pole. Evidence for this glaciation comes from multiple sources. Glacial deposits including diamictites, drop stones in deep water sediments, and glacial striations on bedrock surfaces occur across regions that comprise Gondwana during the late Ordovician, including where now parts of North Africa, South America, and Arabia. The distribution and characteristics of these glacial features indicate ice sheets thousands of meters thick covered substantial portions of the southern supercontinent, with valley glaciers extending into lower latitudes and icebergs calving into the oceans, transporting sediment far from shore before melting and dropping their rocky cargo into deep water muds. The mechanisms triggering this glaciation remain debated, but the leading hypothesis involves the collision and uplift of island arcs and continental fragments during the assembly of Proto-Appalachian Mountains in what is now eastern North America. This mountain-building episode, called the tectonic orogeny, created extensive new highlands with fresh rock surfaces exposed to weathering. The chemical weathering of silicate rocks consumes atmospheric carbon dioxide through reactions that produce dissolved bicarbonate, which ultimately gets transported to the oceans and deposited as carbonate minerals and sediments. If the rate of carbon dioxide consumption through weathering exceeded the rate of volcanic outgassing replenishing atmospheric carbon dioxide, concentrations would decline progressively, weakening the greenhouse effect and cooling the planet. Some researchers have proposed that the evolution of early land plants contributed to the carbon dioxide drawdown. By the late Ordovician, primitive plants, simple non-vascular organisms resembling modern liverworts and mosses, have begun colonizing moist environments on land. These early land plants would have enhanced weathering by secreting organic acids that dissolve rock minerals and by physically breaking apart rock surfaces with their rhizoid structures. Additionally, the burial of plant organic matter on land represented a net removal of carbon from the atmosphere-ocean system. While late Ordovician land plants were far less extensive and diverse than later vegetation, their appearance may have tipped the carbon cycle toward net removal of atmospheric carbon dioxide, accelerating the trend toward cooling already initiated by tectonic uplift and weathering. The extinction proceeded in two distinct pulses corresponding to different phases of the glaciation. The first pulse occurred as ice sheets rapidly expanded and global temperatures plummeted. Sea levels dropped dramatically, possibly by as much as 100 meters, as enormous volumes of water became locked up in continental ice sheets. This sea level fall drained the extensive shallow epicontinental seas that had covered continental interiors throughout the Ordovician, eliminating vast areas of productive habitat. Species adapted to warm, shallow marine environments found their habitats literally disappearing as seas withdrew from continents, leaving only narrow shelves along continental margins. Tropical and subtropical species suffered particularly high extinction rates, unable to migrate to colder conditions or adapt quickly enough to the changing climate. The second extinction pulse occurred during deglaciation, when ice sheets melted and climate warmed again. This might seem counterintuitive. If cooling caused extinction, shouldn't warming provide relief? However, the rapid return to warm conditions created its own problems. Species that had survived the initial cooling by adapting to colder temperatures or retreating to refugia now faced rising temperatures and rising seas flooding back across continental shelves. The rapid pace of environmental change in both directions, first toward cold, then toward warm, prevented many species from adapting. Additionally, the melting ice sheets may have caused ocean stratification and circulation changes that altered nutrient delivery to surface waters, disrupting food webs. The chemistry of the oceans may have shifted as well, with changes in dissolved oxygen levels and carbonate saturation states affecting different groups of organisms. Certain groups suffered disproportionate losses during the late Ordovician extinction. Trilobites, though they survived as a group, lost approximately half their families and never recovered their Ordovician diversity levels, beginning a long decline that would culminate in their complete extinction at the end of the Permian period 250 million years later. Brachiopods experienced severe losses, with many lineages disappearing entirely, though the group recovered in the Silurian and remained important components of marine ecosystems. Bryozoans lost substantial diversity, as did echinoderms, particularly the crinoids and cystoids that had been so diverse during the Ordovician. Graptolites suffered catastrophic losses, with most branching planktonic forms going extinct, though some lineages survived and rediversified in the Silurian. The giant nautiloids, apex predators of Ordovician seas, declined substantially, though they did not disappear completely. Many of the largest straight-shelled species went extinct, possibly because their size and high metabolic demands made them vulnerable to ecosystem collapse and reduced food availability during glaciation. The nautiloids would persist as a group through subsequent periods, occasionally producing large species, but never again achieve the enormous sizes characteristic of the Ordovician giants. Their decline opened ecological space that would eventually be filled by other predators, including jawed fish and eventually marine reptiles in the Mesozoic era. Ironically, the primitive jawless fish that had appeared during the Ordovician generally survived the extinction relatively well compared to many invertebrate groups. Their mostly bottom-dwelling lifestyles and ability to survive in deeper waters may have provided some protection from the most severe environmental changes affecting shallow tropical seas. The survival of these early vertebrates ensured that the vertebrate lineage, still in its infancy during the Ordovician, would continue evolving through subsequent periods, eventually giving rise to jawed fish, amphibians, reptiles, and ultimately dinosaurs. The late Ordovician extinction marked the end of 41 million years of marine diversity expansion and ecological complexity. The Ordovician had seen marine life reach new levels of sophistication, with giant predators, extensive reef systems, and intricate food webs. The glaciation and mass extinction that closed this period demonstrated the vulnerability of even well-established ecosystems to rapid climate change. Yet life proved resilient. During the subsequent Silurian period, marine ecosystems recovered, species diversified again, and evolution continued exploring new possibilities. Most importantly for the eventual history of life, the Silurian would witness the continued colonization of land by both plants and animals, transforming barren continents into habitable ecosystems and setting the stage for the remarkable creatures, giant arthropods, armored fish, and early tetrapods that would characterize the Devonian period ahead. For more than 3 billion years, life had remained confined to the oceans. Land surfaces consisted of barren rock, gravel, and sand, utterly devoid of the green vegetation and teeming animal life that characterizes modern continents. Ultraviolet radiation bathed these lifeless landscapes unfiltered by any protective plant cover or atmospheric ozone layer robust enough to fully shield the surface. Temperatures fluctuated wildly between scorching days and freezing nights without the moderating influence of vegetation and soil. Rivers carved through naked bedrock, their banks empty of roots to stabilize sediments. This desolate world persisted until approximately 440 million years ago, during the Silurian period, when the first pioneers, simple plants, fungi, and arthropods, began the slow transformation of continents from sterile wastelands into habitable ecosystems. The challenges facing these early colonists were formidable. Marine organisms had evolved in an environment where water provided structural support, prevented desiccation, facilitated reproduction through waterborne sperm and eggs, and moderated temperature extremes. On land, organisms faced crushing gravity without water's buoyancy, constant risk of drying out, difficulty reproducing without water to transport gametes, and exposure to temperature swings and intense solar radiation. Successfully transitioning from water to land required fundamental innovations in anatomy, physiology, and reproduction. The organisms that accomplished this transition founded lineages that would eventually include all terrestrial plants, insects, arachnids, and vertebrates including dinosaurs. The first land plants were tiny, non-vascular organisms resembling modern liverworts and mosses. These primitive plants, appearing by the mid-Ordovician and becoming more common in the Silurian, lacked the specialized vascular tissues, xylem and phloem, that transport water and nutrients in more advanced plants. Without these transport systems, early plants remained small, typically just a few centimeters tall, growing in dense mats in moist environments near water, where they could absorb moisture directly through their surfaces. Fossilized spores with distinctive tetrahedral arrangements, characteristic of land plants, appear in rocks dated to approximately 470 million years ago, providing evidence that the colonization of land was already underway by the late Ordovician, though these early pioneers left little other fossil evidence. Cooksonia, one of the earliest well-documented vascular plants, appears in the fossil record during the late Silurian approximately 425 million years ago. This simple plant consisted of thin, branching green stems reaching heights of only a few centimeters, topped with spore-producing structures called sporangia. Cooksonia lacked true leaves and roots, instead possessing simple rhizoids, hair-like structures that anchored the plant and absorbed water and minerals from the substrate. The presence of vascular tissue, however primitive, marked a crucial innovation. The xylem tissue, composed of dead cells whose walls provided both water transport and structural support, allowed Cooksonia to grow taller than non-vascular plants and colonize slightly drier environments away from standing water. The evolution of vascular plants opened vast new territories for colonization and set the stage for the diversification of land flora. Fungi played equally crucial roles in the colonization of land, though their fossil record is sparser than that of plants due to their typically soft tissues. Molecular clock analyses and fragmentary fossil evidence suggest fungi colonized land simultaneously with or even before plants, possibly as early as the Cambrian or Ordovician. Early land fungi likely lived as decomposers, breaking down organic matter, and as symbionts forming mutually beneficial partnerships with early plants. Mycorrhizal associations, symbiotic relationships where fungal filaments colonize plant roots and extend into surrounding soil, appear in some of the earliest land plant fossils. The fungi provided plants with improved access to water and mineral nutrients, particularly phosphorus, while the plants supplied the fungi with sugars produced through photosynthesis. This partnership proved so successful that roughly 90% of modern land plants maintain mycorrhizal associations, suggesting the relationship was crucial for plant colonization of land. The earliest land animals were arthropods, particularly creatures resembling modern millipedes and centipedes. Numidesmus numini, discovered in Scotland in rocks dated to approximately 428 million years ago during the late Silurian, represents the oldest known air-breathing land animal. This millipede-like creature, about 1 centimeter long, possessed specialized breathing structures called spiracles, openings in the body wall that led to internal tubes carrying air directly to tissues. The presence of spiracles indicates Numidesmus had evolved the respiratory adaptations necessary for extracting oxygen from air rather than water, confirming its terrestrial lifestyle. Early millipedes likely fed on decaying plant matter and fungi, filling the crucial ecological role of decomposers in nascent terrestrial ecosystems. Scorpions were among the earliest predatory arthropods to colonize land. While the very earliest scorpion-like creatures may have been marine or amphibious, by the Silurian, scorpions had definitely adapted to terrestrial life. These early scorpions resembled their modern descendants in basic body plan: segmented bodies, 8 legs, pincers for grasping prey, and a curved tail tipped with a venomous stinger. Silurian scorpions reached lengths of several centimeters and likely hunted other small arthropods in the moist environments where early terrestrial communities were establishing themselves. The venom apparatus of scorpions represents one of the earliest examples of chemical weaponry evolving in terrestrial predators, presaging the diverse venomous creatures that would later populate land ecosystems. Other arthropods joining the terrestrial invasion included early relatives of spiders, mites, and primitive wingless insects. These creatures were initially restricted to moist microhabitats, under rocks, within decaying plant matter, or in soil crevices, where humidity remained high and desiccation risk was minimized. The evolution of waterproof cuticles containing waxy compounds helped arthropods resist water loss, while book lungs and tracheal systems evolved to enable air breathing. These physiological innovations, combined with the arthropod exoskeleton, which provided structural support in the absence of water's buoyancy, made arthropods exceptionally well-suited for terrestrial life. By the end of the Silurian period, arthropod communities on land included multiple trophic levels: detritivores feeding on dead plant matter, herbivores consuming living plants, and carnivores preying on other arthropods. The Silurian period, spanning from approximately 444 to 419 million years ago, witnessed climate recovery following the devastating late Ordovician glaciation. Ice sheets melted from Gondwana, sea levels rose again flooding continental margins, and global temperatures climbed to levels warmer than today. Carbon dioxide concentrations remained elevated compared to modern values, maintaining greenhouse conditions. The warm climate and high sea levels created extensive shallow seas surrounding most continents, but also meant large land areas existed in tropical land. Subtropical latitudes where warm temperatures and adequate rainfall provided favorable conditions for the pioneering organisms colonizing terrestrial environments. Marine ecosystems recovered substantially during the Silurian, though they never fully regained the peak diversity of the Middle Ordovician before the mass extinction. Coral and stromatoporoid reefs were rebuilt, creating complex three-dimensional structures that supported diverse communities of invertebrates. Brachiopods remained abundant filter feeders, diversifying into numerous new families to replace those lost during the extinction. Trilobites, though diminished in diversity compared to their Ordovician heyday, still occupied various niches as predators, scavengers, and deposit feeders. Graptolites, devastated by the Ordovician extinction, rediversified but with reduced morphological variety. Most surviving forms were simple, unbranched planktonic types rather than the elaborate branching colonies of the Ordovician. The most significant development in Silurian marine ecosystems was a diversification of jawed fish. The Ordovician seas had been dominated by jawless armored fish and giant nautiloid predators, but during the Silurian, fish with true jaws, gnathostomes, appeared and began diversifying. Jaws evolved from the interior gill arches of jawless fish ancestors, transforming structures originally used for filter feeding and respiration into powerful biting and grasping devices. This innovation revolutionized vertebrate ecology, allowing fish to pursue active predation on a wide variety of prey rather than being restricted to filtering or sucking up food particles. The evolution of jaws ranks among the most consequential events in vertebrate history, as all subsequent fish, amphibians, reptiles, birds, and mammals descend from these early jawed fish. Two major groups of jawed fish diversified during the Silurian, the placoderms and the acanthodians. Placoderm, whose name means plate-skinned, were armored fish bearing heavy bony plates covering their heads and anterior bodies, with the posterior portions either naked or covered in scales. These fish ranged from small bottom dwellers, just a few centimeters long, to larger predatory forms approaching 1 meter in length by the late Silurian. Placoderms would achieve their greatest size and diversity during the subsequent Devonian period, producing some of the ocean's most fearsome predators. Acanthodians, sometimes called spiny sharks though not closely related to true sharks, were small fish typically 10 to 20 centimeters long, characterized by distinctive spines preceding each fin. These fish likely fed on small prey and organic particles, occupying ecological niches similar to modern small fish. True sharks, members of the class Chondrichthyes, characterized by skeletons of cartilage rather than bone, also appear during the Silurian, though their early fossil record is fragmentary since cartilage preserves poorly. The earliest shark-like scales appear in Silurian rocks, and by the end of the period, primitive sharks were established members of marine communities. These early sharks differed from modern forms in many respects but shared the basic characteristics: cartilaginous skeletons, multiple gill slits, and teeth that were continuously replaced throughout life. The success of sharks, which have persisted relatively unchanged for over 400 million years, demonstrates the effectiveness of their body plan for predatory life in marine environments. The Silurian ended approximately 419 million years ago, without a major mass extinction, transitioning smoothly into the Devonian period. The Devonian, lasting from 419 to 359 million years ago, is often called the Age of Fishes due to the extraordinary diversification and ecological dominance of fish during this interval. However, for the history of terrestrial life and the eventual evolution of dinosaurs, the Devonian's most important developments occurred on land, where plants underwent a dramatic radiation that transformed barren continents into forested landscapes, and where the first vertebrates began their tentative exploration of terrestrial environments. The early Devonian witnessed explosive diversification of vascular plants. While Silurian vegetation had consisted primarily of small, primitive plants hugging moist substrates, Devonian plants evolved into progressively larger and more complex forms. By the Middle Devonian around 390 million years ago, forests had appeared for the first time in Earth's history. These were not forests in the modern sense. The trees were primitive plants unrelated to modern trees, but they represented woodland ecosystems with closed canopies, vertical structure, and complex ecological interactions. The appearance of forests fundamentally altered Earth's terrestrial environments, creating new habitats, moderating climate, promoting soil formation, and changing patterns of weathering and erosion. Rhinophytes, a group of early vascular plants named after the Rhynie chert in Scotland where exceptionally well-preserved fossils occur, dominated early Devonian vegetation. These plants, slightly more advanced than Silurian forms like Cooksonia, possessed branching stems up to about 50 centimeters tall with primitive vascular tissue and sporangia at the tips of branches. The Rhynie chert, dated to approximately 410 million years ago, preserves plants in extraordinary cellular detail through silicification, infiltration of plant tissues by silica-rich water from hot springs that rapidly entombed and preserve the organisms. This exceptional preservation reveals internal structures including vascular tissue, spores, and even fungi forming mycorrhizal associations with plant roots, providing unparalleled insight into early terrestrial ecosystem structure. Lycophytes, ancestors of modern club mosses, evolved during the early Devonian and would eventually produce some of the largest trees of the later Devonian and Carboniferous periods. Early lycophytes like Baragwanathia, appearing approximately 420 million years ago, possessed leaves, actually leaf-like scales called microphyls that evolved from simple outgrowths of the stem. These plants grew as small creeping or upright forms in moist environments. The evolution of leaves, even primitive ones, represented a major innovation, increasing the surface area available for photosynthesis and improving plants' ability to capture light energy. Throughout the Devonian, lycophytes would evolve into increasingly large forms, eventually producing trees reaching heights of 30 meters or more in Carboniferous coal swamps. The Mid-Devonian marked the appearance of the first plants with true leaves derived from flattened branch systems, a group that included the ancestors of ferns and seed plants. These progymnosperms possessed wood-producing cambium tissue that allowed them to grow thick, strong trunks and reach substantial sizes. Archaeopteryx, appearing around 385 million years ago in the late Devonian, grew as a tree reaching heights of 20 to 30 meters with a trunk diameter up to 1.5 meters. These trees bore fern-like fronds for leaves and reproduced via spores like ferns, yet their woody trunks resembled those of seed plants. Archaeopteryx forests spread across Devonian continents, creating the first extensive woodland ecosystems and marking a threshold in Earth's terrestrial transformation. The ecological consequences of Devonian forest development were profound. Plant roots penetrated bedrock and soil, physically breaking apart rock and accelerating weathering through secretion of organic acids. This enhanced weathering consumed atmospheric carbon dioxide at accelerated rates, likely contributing to a gradual decline in carbon dioxide concentrations and consequent cooling over the course of the Devonian. Fallen plant material accumulated on forest floors, supporting communities of decomposer organisms including fungi, bacteria, and detritivorous arthropods. For the first time, substantial amounts of organic carbon were being buried on continents rather than only in marine sediments, representing a significant change in the global carbon cycle. Soil formation accelerated dramatically with the spread of forests. Prior to widespread plant colonization, weathered rock material on continents consisted mainly of mineral particles with minimal organic content. Plant roots, leaf litter, and the activities of soil-dwelling organisms created true soils with organic-rich upper layers supporting complex microbial and fungal communities. Soil formation had cascading effects. It retained moisture, supported denser plant communities, provided habitat for burrowing organisms, and altered patterns of erosion and sediment transport to the oceans. Rivers draining forested landscapes carried different sediment loads and nutrient compositions than rivers flowing across barren rock, changing the chemistry and productivity of coastal marine environments. Arthropods diversified extensively in Devonian terrestrial ecosystems, taking advantage of the increasing abundance and variety of plant material and the expanding habitat complexity created by vegetation. Millipedes grew larger, with some species reaching lengths of 10 to 20 centimeters, feeding on decaying plant matter and forest floor litter. Early insects appeared, including primitive, wingless forms resembling modern silverfish. These early insects likely fed on decaying vegetation, fungi, and organic debris. The evolution of wings in insects would not occur until the later Devonian or early Carboniferous, but the stage was being set for the eventual diversification of insects into the most diverse group of animals on Earth. Spiders had definitively colonized land by the Devonian. A Turcopus from approximately 380 million years ago represents one of the earliest known spiders, possessing spinnerets for producing silk, though it lacked the specialized structures for weaving the organized webs characteristic of many modern spiders. Early spiders likely used silk to line burrows, create drag lines for safety during movement, and wrap egg cases, establishing the foundation for the diverse silk-using behaviors that would later evolve. As predators feeding on other arthropods, spiders filled important ecological roles in Devonian terrestrial food webs. The late Devonian witnessed one of the most important transitions in vertebrate evolution, the emergence of tetrapods, four-limbed vertebrates that would give rise to all amphibians, reptiles, birds, and mammals. The earliest tetrapods evolved from lobe-finned fish possessing fleshy, bone-supported fins rather than the thin, ray-supported fins of most fish. These lobe-finned fish included lungfish, which could breathe air using lungs in addition to gills, and the coelacanth and their extinct relatives. In certain environments, shallow, vegetation-choked swamps and seasonal pools subject to low oxygen levels, the ability to breathe air and use muscular fins to move through dense vegetation or across short stretches of land provided significant advantages. Tiktaalik, discovered in Arctic Canada and rocks dated to approximately 375 million years ago, represents a transitional form between lobe-finned fish and early tetrapods. This creature reached lengths of 1.5 to 2.5 meters and possessed a mixture of fish and tetrapod characteristics. Its head was flattened like a crocodile's with eyes on top, suitable for lurking in shallow water, watching for prey above. It possessed gills for breathing underwater, and likely had lungs for air breathing. Most significantly, Tiktaalik's pectoral fins contained bones homologous to the humerus, radius, and ulna of tetrapod forelimbs, and these fins were robust enough to support the animal's weight, allowing it to prop itself up in shallow water or possibly make short excursions onto mudflats or riverbanks. By the very end of the Devonian, approximately 365 million years ago, true tetrapods with digits rather than fins had appeared. Acanthostega and Ichthyostega from Greenland possessed 8 and 7 digits respectively on their limbs, along with fish-like tails and other aquatic adaptations. These early tetrapods likely spent most of their time in water, using their limbs to move through dense aquatic vegetation, but they had crossed the threshold to life on land. The evolutionary transition from fish to tetrapod represents one of the most significant events in the history of life, as it established the vertebrate lineage from which dinosaurs would eventually emerge. The Devonian period ended approximately 359 million years ago, with a series of extinction pulses collectively called the Late Devonian extinctions. These events, spread over perhaps 20 million years, eliminated approximately 75% of species, particularly affecting marine organisms. Reef ecosystems collapsed, with stromatoporoids and many corals going extinct. Armored fish, including most placoderms, disappeared. The causes remain debated but likely involved climate change, ocean anoxia, oxygen depletion in deep waters, and possibly asteroid impacts. Importantly, terrestrial ecosystems suffered less severe impacts than marine environments, allowing plants and early terrestrial animals to continue their diversification into the subsequent Carboniferous period. By the close of the Devonian, Earth's continents had been utterly transformed. Where once barren rock had dominated, forests now grew, some reaching 30 meters tall. Soils carpeted the ground, supporting complex communities of plants, fungi, and arthropods. Rivers flowed between vegetated banks, carrying sediments and nutrients altered by interactions with living organisms. Early tetrapods had begun exploring terrestrial environments, establishing the vertebrate presence on land that would expand dramatically in subsequent periods. The stage was set for the Carboniferous period, when oxygen levels would soar, allowing arthropods to achieve gigantic sizes, and when the first amniotic eggs would free vertebrates completely from dependence on water for reproduction, paving the way toward reptiles and eventually dinosaurs. The Devonian period, spanning from 419 to 359 million years ago, earned its popular nickname the Age of Fishes through the explosive diversification and ecological dominance of fish in both marine and freshwater environments. While previous chapters have touched on the early evolution of jawed fish during the Silurian, the Devonian witnessed their transformation into the rulers of Earth's oceans, lakes, and rivers. Among these diverse fish groups, one lineage stood apart in terms of sheer ferocity and anatomical innovation: the placoderms, armored fish that would produce some of the most formidable predators in the history of marine life. These creatures combined massive size with crushing bite forces, revolutionary jaw mechanics, and heavy bony armor that made them nearly invulnerable to attacks from other predators. Placoderms had appeared during the late Silurian as relatively small armored fish, but during the Devonian they underwent dramatic size increases and ecological diversification. The defining characteristic of placoderms was their armor: thick bony plates covering the head and thorax, articulated through a ball-and-socket joint that allowed the head shield to move relative to the body shield. This articulation gave placoderms enhanced jaw mobility compared to earlier armored fish. The posterior portion of the body was either naked or covered with smaller scales, providing flexibility for swimming. By the Middle and Late Devonian, placoderms had diversified into multiple families occupying varied ecological niches, from small bottom-dwelling forms just a few centimeters long to apex predators reaching lengths of 6 meters or more. The arthrodires, meaning jointed necks, represented the most diverse and successful placoderm group, comprising roughly 60% of all known placoderm species. These fish bore the characteristic articulated joint between head and body shields, which allowed them to open their mouths wider than would otherwise be possible given the constraints imposed by heavy armor. Early arthropods were relatively small, but as the Devonian progressed, certain lineages evolved into increasingly large predatory forms. The Late Devonian seas, approximately 360 to 355 million years ago, were dominated by gigantic arthropods that ranked among the ocean's most fearsome inhabitants. Dunkleistus torelli, named after paleontologist David Dunkel, represents the most famous and arguably most formidable of all placoderms. This massive predator, known primarily from fossils found in the Cleveland Shale of Ohio and equivalent formations in other regions, reached estimated lengths of 6 to 8.5 meters, with some researchers proposing even larger maximum sizes potentially, approaching 10 meters. The head shield alone measured up to 1 meter in length, housing a brain case and sensory organs within thick protective bone. The body, though less well preserved in most fossils due to lack of heavy armor in the posterior regions, was likely muscular and streamlined for pursuit predation. The most remarkable feature of Dunkleistus was its jaw apparatus. Unlike modern jawed vertebrates that possess teeth anchored in sockets within the jawbones, placoderms lacked true teeth. Instead, the bones of the jaw itself were modified into sharp, self-sharpening, blade-like edges. In Dunkleistus, these bone blades formed at the front of the jaw, with one pair on the upper jaw and another on the lower jaw. As the jaws closed, the blades slid past each other like scissor blades, capable of shearing through armor, bone, and flesh with devastating efficiency. The continuous use and wear of these blades kept their edges sharp, and as the fish grew, the blades grew as well, maintaining their lethal effectiveness throughout the animal's life. Biomechanical studies of Dunkleistus jaw mechanics, based on detailed analysis of fossil skull remains and computer modeling, have revealed extraordinary bite forces. Research published in the early 21st century estimated that Dunkleistus could generate bite forces exceeding 4,400 newtons at the tip of its jaws, with forces potentially reaching 11,000 newtons at the blade base. To put this in perspective, these values rival or exceed the bite forces of large modern crocodiles and approach the estimated bite forces of Tyrannosaurus rex, making Dunkleistus one of the most powerful biters in the entire fossil record relative to its size. The speed of jaw closure was equally impressive, with estimates suggesting Dunkleistus could snap its jaws shut in approximately 50 milliseconds, generating powerful suction that could draw prey into its mouth. The feeding ecology of Dunkleistus can be inferred from several lines of evidence. Fossilized remains of other fish, including placoderms, have been found in association with Dunkleistus fossils, some showing evidence of having been bitten by powerful jaws. Additionally, researchers have discovered regurgitated stomach contents, fossilized vomit, containing partially digested fish bones near Dunkleistus specimens, suggesting these predators sometimes expelled indigestible hard parts after consuming prey. The ability to bite through armor meant Dunkleistus could prey on other armored fish, including smaller placoderms, giving it access to food sources unavailable to predators with weaker bite forces. This apex predator position would have made adult Dunkleistus virtually unchallenged in late Devonian seas. Other large arthropods share the Devonian oceans with Dunkleistus. Titanichthyes, despite reaching lengths comparable to Dunkleistus at 4.5 to 5 meters or possibly larger, possessed much weaker jaws lacking the sharp bone blades characteristic of predatory arthropods. Instead, Titanichthyes is interpreted as a filter feeder, using its large gape to strain small prey and organic particles from the water, essentially filling the ecological niche occupied by modern baleen whales and basking sharks. The existence of gigantic filter-feeding placoderms alongside gigantic predatory forms demonstrates the ecological diversity achieved by these armored fish during their Devonian heyday. Coccysteus, a smaller arthrodire typically 30 to 40 centimeters long, was abundant in Devonian freshwater and brackish environments. Thousands of well-preserved specimens have been found in the Old Red Sandstone deposits of Scotland and other regions, providing detailed information about placoderm anatomy and life history. Coccysteus possessed the typical arthropod body plan, heavy head and thorax armor with flexible posterior body, and likely fed on smaller fish, invertebrates, and organic debris. The abundance of Coccysteus fossils suggests these mid-sized placoderms were successful predators in their ecosystems, occupying ecological roles similar to modern pike or bass in freshwater systems. Beyond the arthrodires, other placoderm groups exhibited remarkable diversity in body form and ecology. The antiarchs, characterized by distinctive pectoral fins enclosed in bony armor and jointed like crab legs, were primarily small bottom-dwelling fish that fed on organic material and sediments. These bizarre-looking creatures, which superficially resembled armored crabs more than fish, were abundant in both marine and freshwater environments during the Middle and Late Devonian. Bothriolepis, one of the most common antiarch genera, reached lengths of about 30 centimeters and has been found on every continent except Antarctica, demonstrating the wide geographic distribution achieved by some placoderm groups. The rhenanids and philolepids represent placoderm groups that adapted to ray-like lifestyles, developing flattened bodies with expanded pectoral fins for gliding along the seafloor. These dorsoventrally compressed placoderms likely ambushed prey from the sediment surface or fed on bottom-dwelling invertebrates, filling ecological niches similar to modern skates and rays. Their flattened armor showed adaptations for benthic life, with eyes positioned on top of the head and mouth facing downward. The convergent evolution of ray-like body forms in placoderms, true rays, which are cartilaginous fish, and even some bony fish demonstrates that this body plan represents an effective solution for bottom-dwelling predatory lifestyles. While placoderms dominated as large predators, they share Devonian waters with increasingly diverse members of other fish groups. True sharks, cartilaginous fish of the class Chondrichthyes, continue diversifying from their Silurian origins. These early sharks differ from modern forms in many details but share the basic characteristics: skeletons of cartilage, 5 to 7 pairs of gill slits, and continuously replaced teeth. Cladoslake from the late Devonian Cleveland Shale reached lengths of up to 2 meters and possessed a streamlined body with large eyes, suggesting it was an active pursuit predator. Unlike modern sharks, Cladoslake lacked claspers, reproductive structures in males, and had unusual fin structures, indicating that many shark anatomical features familiar today had not yet evolved. The acanthodians, or spiny sharks, remained common and diverse throughout the Devonian. These small to medium-sized fish, typically 10 to 30 centimeters long though some species reached larger sizes, were characterized by spines preceding each fin. Acanthodians occupied various ecological niches as small predators and prey species, forming important components of both marine and freshwater food webs. Recent analyses of acanthodian anatomy have suggested they may not form a single natural group but rather represent a paraphyletic assemblage of early jawed fish lineages, some more closely related to modern bony fish and others to cartilaginous fish, indicating the early jawed fish radiation was more complex than previously understood. The osteichthyons, or bony fish, underwent their own explosive radiation during the Devonian, establishing the lineages that would eventually dominate aquatic environments after the placoderm's extinction. Two major groups emerged, the actinopterygians, ray-finned fish, and the sarcopterygians, lobe-finned fish. Ray-finned fish, which today comprise roughly 96% of all fish species, began their rise to dominance during the Devonian. Early ray fins were relatively small predators with thick scales and heavy bones, quite different from many modern forms that have thin scales and lighter skeletons. These Devonian ray fins explored both marine and freshwater habitats, establishing the foundational body plan that would later diversify into the extraordinary variety of modern fish from seahorses to tuna to anglerfish. The lobe-finned fish, though far less diverse today with only coelacanth and lungfish surviving, were abundant and varied during the Devonian. These fish possessed muscular, bone-supported fins rather than the thin ray-supported fins of actinopterygians, and many possessed lungs or lung-like structures for air breathing in addition to gills. The lobe-finned fish are significant beyond their Devonian diversity because one lineage gave rise to tetrapods, the four-limbed vertebrates including amphibians, reptiles, birds, and mammals. The robust fins of lobe-finned fish, containing bones homologous to the limb bones of tetrapods, pre-adapted them for supporting weight and movement in shallow water environments, facilitating the eventual transition to land that occurred in the late Devonian. Freshwater environments during the Devonian supported diverse fish communities, distinct from marine assemblages. Rivers, lakes, and estuaries hosted specialized fish faunas including numerous placoderms, lobe-finned fish, and early ray-finned fish adapted to the challenges of freshwater life, variable salinity, seasonal flow changes, and sometimes low oxygen levels. The Old Red Sandstone, a distinctive sedimentary formation deposited across vast areas of the Devonian supercontinent Euramerica, preserves exceptional records of these freshwater ecosystems. Fossil fish from the Old Red Sandstone include armored placoderms, lobe-finned fish with well-developed lungs, and early representatives of groups that would later colonize land. The paleogeography of the Devonian created conditions favorable for fish diversification. Sea levels stood very high throughout most of the period, flooding continental interiors and creating extensive shallow epicontinental seas, vast areas of warm, relatively shallow water covering what are now dry land. These shallow seas provided enormous expanses of productive habitat where photosynthetic organisms thrived and food webs flourished. The warm climate, with tropical conditions extending to higher latitudes than today, and no polar ice caps for most of the Devonian, meant marine habitats were widely distributed across diverse latitudes. The collision of the paleocontinents Laurentia and Baltica to form Euramerica, and the ongoing approach of Gondwana toward Euramerica that would eventually form the supercontinent Pangaea, created active tectonic margins with associated mountain building, which in turn produced varied coastal environments and deep ocean basins. The dominance of placoderms and the remarkable diversity of Devonian fish came to an abrupt end during a series of extinction events collectively called the Late Devonian extinctions. Unlike many mass extinctions that occurred rapidly in geological terms, the Late Devonian crisis unfolded over approximately 20 million years, from roughly 375 to 359 million years ago, with multiple discrete pulses of biodiversity loss separated by intervals of partial recovery. The most severe pulses occurred during the Kellwasser events in the late Frasnian stage, approximately 372 million years ago, and the Hangenberg event at the very end of the Devonian, approximately 359 million years ago. Together, these extinction pulses eliminated approximately 70 to 75% of all species and roughly 19% of families. The causes of the late Devonian extinctions remain actively debated, with evidence pointing to multiple contributing factors rather than a single catastrophic trigger. Climate change, particularly cooling episodes that reduced ocean temperatures, appears to have played a significant role. Evidence for glaciation in the southern supercontinent Gondwana during the latest Devonian indicates substantial ice sheet growth, which would have lowered global sea levels and eliminated shallow marine habitats as seas withdrew from continental shelves. The cooling may have been triggered by the spread of forests on land, which consumed atmospheric carbon dioxide through photosynthesis and enhanced weathering through root activity and organic acid secretion, weakening the greenhouse effect and driving global temperatures downward. Ocean anoxia, depletion of dissolved oxygen in seawater, affected many marine environments during the late Devonian extinction intervals. Black shale deposits rich in organic matter and lacking signs of bottom-dwelling organisms occur globally in rock formations corresponding to the extinction pulses, indicating that large areas of seafloor became oxygen-depleted dead zones. The anoxia may have resulted from stratification of the water column, where warm surface waters prevented mixing with cooler, oxygen-rich deep waters, allowing organic matter to accumulate and consume available oxygen during decomposition. Alternatively, increased nutrient runoff from weathering of the newly forested continents may have stimulated algal blooms that subsequently depleted oxygen when they died and decayed. Areas of anoxic water would have been uninhabitable for most animals, eliminating populations and fragmenting habitats. The extinctions hit certain groups disproportionately hard. Placoderms, which had dominated as predators and achieved remarkable diversity during the Devonian, were completely eliminated by the end of the period. Not a single placoderm species survived into the Carboniferous. The extinction of these armored fish removed the top predators from many marine ecosystems and opened ecological niches that would eventually be filled by sharks and large ray-finned fish. The loss of placoderms meant the end of an entire class of vertebrates, one of only a handful of vertebrate classes to have gone completely extinct since the origin of jawed vertebrates. Their reign had lasted roughly 70 million years from their first appearance to their final extinction. Reef ecosystems suffered catastrophic losses during the late Devonian extinctions. The stromatoporoid sponges that had been major reef builders since the Ordovician were devastated, losing most species. Rugose and tabulate corals, the other major reef-forming groups, declined severely. Following the Kellwasser events, reef ecosystems essentially collapsed globally, with reef communities taking millions of years to recover and never quite regaining their Devonian complexity until new reef-building organisms evolved in later periods. The loss of reef habitats eliminated the complex three-dimensional structures that supported diverse communities of invertebrates, further magnifying the extinction's impact. Trilobites, already in decline since the late Ordovician extinction, lost additional diversity during the late Devonian events. Several major trilobite families disappeared entirely. Ammonoids, cephalopod mollusks with coiled shells that had diversified during the Devonian, suffered severe losses, with all but one or two groups going extinct during the Kellwasser events. However, ammonoids demonstrated remarkable resilience by rediversifying rapidly from the surviving lineages during the Carboniferous, illustrating that extinction events can sometimes create opportunities for surviving groups to radiate into emptied ecological niches. Significantly for the eventual evolution of dinosaurs, the late Devonian extinctions affected marine environments far more severely than terrestrial ecosystems. Land plants, which had undergone explosive diversification during the Devonian to create the first forests, generally survived the extinction pulses with minimal disruption. Terrestrial arthropods and the early tetrapods that had recently colonized land also weathered the crisis relatively well. This differential impact meant that while marine ecosystems were devastated and would require millions of years to recover, terrestrial ecosystems continued their development relatively uninterrupted, allowing the continued evolution of land plants and animals through the subsequent Carboniferous period. By the close of the Devonian, approximately 359 million years ago, the age of armored fish had ended. The massive placoderms that had ruled as apex predators for tens of millions of years were gone, their ecological roles vacant. Sharks and bony fish inherited the oceans, beginning the long evolutionary trajectory that would establish them as the dominant aquatic vertebrates for the next 360 million years up to the present day. On land, forests stretch across continents, their canopies rustling with arthropod life, and their waterways hosting the early tetrapods that would soon give rise to true terrestrial vertebrates. The next chapter of Earth's pre-dinosaurian history, the Carboniferous period, would see oxygen levels soar to unprecedented heights, allowing arthropods to achieve gigantic sizes and enabling the diversification of early tetrapods into forms that would eventually produce reptiles, synapsids, and ultimately the dinosaurs that would appear more than 150 million years in the future. The Carboniferous period, spanning from approximately 359 to 299 million years ago, witnessed Earth's atmosphere undergo a dramatic transformation that would enable life to achieve sizes never seen before or since. Atmospheric oxygen levels climbed to unprecedented concentrations, reaching approximately 35% of the atmosphere, compared to today's 21%. This oxygen enrichment resulted from the explosive spread of vast forested swamps, covering tropical and subtropical regions of the supercontinent that was gradually assembling through the collision of major landmasses. The forests produced enormous quantities of plant material through photosynthesis, releasing oxygen into the atmosphere, while much of this organic matter became buried in waterlogged sediments before it could decay and consume oxygen through decomposition. The result was a world where breathing was easier, fires burned hotter, and most remarkably, arthropods could grow to absolutely monstrous proportions. The size limits of arthropods are fundamentally constrained by their respiratory system. Unlike vertebrates that possess lungs and circulatory systems to transport oxygen throughout the body via hemoglobin and blood, arthropods breathe through a tracheal system, a network of tubes called tracheae that carry air directly from openings in the exoskeleton called spiracles to internal tissues. This system works through passive diffusion rather than active pumping in most arthropods, and diffusion becomes increasingly inefficient as body size increases and the distance oxygen must travel grows longer. In today's atmosphere with 21% oxygen, this constraint limits terrestrial arthropods to relatively modest sizes. The largest modern arthropods include tarantulas with leg spans of about 30 centimeters and stick insects reaching lengths of around 60 centimeters. However, in the oxygen-rich Carboniferous atmosphere, diffusion worked far more efficiently because the higher concentration gradient allowed oxygen to penetrate deeper into tissues, removing the size constraint and permitting arthropods to achieve dimensions that would be physiologically impossible in modern atmospheric conditions. Arthropleura, a massive millipede-like creature, represents the largest known land arthropod in Earth's history. Fossil trackways and body fossils from Carboniferous deposits in Europe and North America reveal animals reaching lengths of 2 to 2.5 meters and possibly even larger, with body widths of approximately 45 centimeters. These enormous creatures possess segmented bodies with dozens of leg-bearing segments, each segment bearing 2 pairs of legs for a total of 60 to 80 legs or more depending on the number of body segments. The exoskeleton was composed of hard chitinous plates that have been preserved in exceptional detail in some specimens, showing the articulation between segments that allowed the animal to move with surprising flexibility despite its massive size. Arthropleura trackways discovered in fossil deposits show that these giants walked with their legs positioned somewhat underneath their bodies, rather than splayed out to the sides like modern millipedes, suggesting they could support their considerable weight effectively. The feeding ecology of Arthropleura remains somewhat uncertain due to the lack of preserved mouthparts in most specimens, but several lines of evidence suggest these giants were herbivores or detritivores feeding on the abundant plant material carpeting Carboniferous forest floors. The environments where Arthropleura fossils occur typically represent forested floodplains with dense vegetation, and fossilized plant material is often associated with the animal remains. Some researchers have proposed that Arthropleura may have possessed grinding mouthparts similar to modern millipedes, allowing them to consume leaf litter, dead wood, and possibly living plants. The enormous size of these creatures would have required substantial food intake to maintain their metabolism, and the luxuriant Carboniferous forests provided abundant plant resources to support such massive herbivores. The skies above Carboniferous swamps were patrolled by equally impressive giants. Meganeura and related griffinflies, often called giant dragonflies though they belong to a related but distinct order called Meganosoptera, achieved wingspans of up to 70 to 75 centimeters, making them the largest known flying insects in Earth's history. These aerial predators possessed four wings that could operate independently, allowing remarkable maneuverability during flight. Large compound eyes provided excellent vision for hunting, while powerful mandibles equipped with sharp tooth-like projections could grasp and process prey. The body was elongated and streamlined, with a segmented abdomen and robust thorax housing the powerful flight muscles that drove the wings. Meganeura and its relatives were voracious predators, feeding on other flying insects and possibly even small terrestrial vertebrates. Fossil evidence and anatomical reconstruction suggest these griffinflies were ambush predators that could hover in place or execute rapid acceleration to intercept prey. The high oxygen levels not only allowed their large size, but also would have supported the high metabolic rates required for powered flight at such dimensions. Modern insects rarely exceed 15 centimeters in wingspan, partly due to the physiological challenges of flying in lower oxygen concentrations and partly due to the weight of it. Exoskeletons scaling unfavorably with size. Carboniferous atmospheric conditions remove these constraints temporarily, allowing a brief window in geological time when insect gigantism flourished. Predatory arthropods on the ground included scorpions and other arachnids that achieved sizes far exceeding their modern relatives. Pulmonoscorpius, a scorpion from the early Carboniferous of Scotland, reached lengths of approximately 70 centimeters, roughly the size of a small dog. This fearsome predator possessed the characteristic scorpion body plan with pincers for grasping prey, 8 walking legs, and a segmented tail curving over the back and tipped with a venomous stinger. The venom apparatus of Carboniferous scorpions likely functioned similarly to modern scorpions, injecting neurotoxic or cytotoxic compounds to subdue prey and defend against threats. Giant scorpions would have been apex predators in the leaf litter and understory of Carboniferous forests, hunting smaller arthropods and possibly even juvenile amphibians or early reptiles. Spiders of impressive size also inhabited Carboniferous ecosystems, though determining maximum sizes from fragmentary fossils remains challenging. Well-preserved spider fossils from Carboniferous coal deposits show animals with body lengths of several centimeters and leg spans potentially reaching 15 to 20 centimeters or more. These early spiders had already evolved silk-producing spinnerets and likely used silk for various purposes including lining burrows, creating safety lines during movement, and possibly constructing simple webs to trap prey, though the complex orb webs characteristic of many modern spiders may not have evolved until later periods. The diversity of spiders increased substantially during the Carboniferous as they exploited the abundant insect prey available in expanding forests. The forests that supported this megafauna of giant arthropods differed dramatically from any woodland ecosystem existing today. The dominant trees were not flowering plants or conifers but rather enormous lycophytes, relatives of modern club mosses, which today grow as small herbaceous plants rarely exceeding 30 centimeters in height. Carboniferous lycophytes, particularly Lepidodendron and Sigillaria, evolve into massive trees reaching heights of 30 to 40 meters with trunk diameters of 1 to 2 meters. These trees possessed a distinctive appearance that would seem alien to modern eyes. The trunks were covered in a diamond-shaped pattern of leaf scars where photosynthetic leaves had attached before falling off as the tree grew upward. The top of the trunk bore a crown of long grass-like leaves that carried out photosynthesis, while the roots consisted of specialized underground organs called stigmaria that spread horizontally through the waterlogged soil. Lepidodendron, whose name means scale tree in reference to the bark pattern, reproduced through spores rather than seeds. At maturity, these trees produced enormous cone-like structures at their branch tips that released millions of spores into the environment. The spores would settle in moist conditions and germinate into small, independent gametophyte plants that produced eggs and sperm. Fertilization required water for the sperm to swim to eggs, restricting these trees to wet environments. Once fertilized, the resulting embryo would grow into a new sporophyte tree, completing the life cycle. This reproductive strategy, inherited from their moss-like ancestors, worked effectively in the perpetually wet Carboniferous swamps, but would prove a vulnerability when climate conditions eventually changed. The internal anatomy of lycophyte trees reflected their evolutionary heritage and ecological requirements. Unlike modern trees that produce strong dents with through secondary growth from a vascular cambium, lycophyte trees generated their thick trunks through a different mechanism. They possessed relatively thin cylinders of vascular tissue surrounded by thick layers of outer cortex tissue. Essentially, the trunk consisted mostly of outer bark with limited internal woody support. This construction was sufficient in the waterlogged swamp environments where the saturated soil provided lateral support for the roots, preventing the trees from toppling despite their relatively weak trunk structure. However, this anatomy meant that when these trees died and fell, they often remained intact rather than being broken apart by decomposers, contributing to the accumulation of organic matter that would eventually form coal. Tree ferns constituted another major component of Carboniferous forests, growing as medium-sized trees reaching heights of 10 to 15 meters. These early ferns resembled modern tree ferns in basic form, with a central trunk consisting of matted adventitious roots surrounding a core of vascular tissue, topped by a crown of large compound fronds. The ferns occupied the understory beneath the towering lycophyte canopy, creating a multi-layered forest structure. Additional diversity came from various seed ferns, plants that superficially resembled ferns with their compound leaves but reproduced via seeds rather than spores, representing an evolutionary intermediate between spore-bearing plants and modern seed plants. Horsetails, relatives of modern equisetum, grew as trees reaching heights of 15 to 20 meters in some species, with distinctive jointed stems and whorls of branches at each joint. The forest floor was perpetually wet, covered with decaying plant matter, and teeming with arthropod life. Layers of fallen leaves, dead wood, and organic debris accumulated to substantial depths in areas with poor drainage. This organic accumulation occurred because the organisms responsible for decomposing wood in modern forests, particularly fungi capable of breaking down lignin, the complex polymer that gives wood its structural strength, had not yet evolved the full suite of enzymes necessary to efficiently decompose the particular lignin chemistry of Carboniferous lycophyte trees. White rot fungi, which today play crucial roles in wood decomposition, evolved their lignin-degrading capabilities later, possibly during or after the Carboniferous. The combination of waterlogged conditions that slow decomposition and the absence of efficient decomposers meant that enormous volumes of plant material were buried and eventually transformed through heat and pressure into coal, the fossil fuel that gives the Carboniferous its name, derived from the Latin word for coal. The coal deposits formed during the Carboniferous period represent the most extensive coal-forming episode in Earth's history. Thick seams of coal occurring in Europe, eastern North America, and other regions that occupied tropical latitudes during the Carboniferous preserve the remains of these ancient swamp forests compressed and altered by geological processes. The coal formed through a progression. First, plant material accumulated as peat in waterlogged swamps. Then, as sediments buried the peat and tectonic forces compressed the deposits, the organic matter underwent chemical and physical changes, losing water and volatile compounds while increasing in carbon concentration, transforming progressively from peat to lignite to bituminous coal and finally, in some cases, to anthracite coal. Mining and burning these coal deposits over the past 2 centuries has released carbon that was sequestered from the Carboniferous atmosphere hundreds of millions of years ago, contributing to modern climate change. The climate of the Carboniferous was not uniform globally. Tropical and subtropical regions where the coal swamps flourished experienced warm, humid conditions year-round with high rainfall, supporting the luxuriant forests. However, the gradual assembly of the supercontinent Pangaea through continental collisions was creating increasingly large landmasses with continental interiors far from oceanic moisture sources. These interior regions developed more seasonal climates with distinct wet and dry periods, and at higher latitudes, particularly in the southern supercontinent Gondwana, glaciation occurred during the late Carboniferous, creating a major ice age that would extend into the subsequent Permian period. This climate variation from tropical forests to glaciated poles created diverse environmental zones supporting different biological communities. Vertebrate life underwent crucial evolutionary advances during the Carboniferous that would prove essential for the eventual evolution of dinosaurs. Early tetrapods, 4-limbed vertebrates that had originated in the late Devonian, diversified extensively during the Carboniferous, splitting into multiple major lineages. These early tetrapods were still tied to aquatic environments for reproduction, as they laid eggs in water, and their larvae underwent aquatic development before metamorphosing into terrestrial or semi-terrestrial adults, similar to modern frogs and salamanders. However, during the Carboniferous, one lineage evolved a revolutionary adaptation that would free vertebrates completely from dependence on water: the amniotic egg. The amniotic egg represents one of the most important innovations in vertebrate history. Unlike the eggs of fish and amphibians, which must be laid in water to prevent desiccation, the amniotic egg possessed several specialized membranes and a protective shell that allowed it to be laid on land. The amnion membrane surrounded the embryo in a fluid-filled sac, providing an aquatic environment for development even on dry land. The chorion and allantois membranes facilitated gas exchange and waste storage. The shell, whether leathery as in many modern reptiles or mineralized as in birds, protected the embryo from physical damage and prevented water loss while remaining permeable to oxygen and carbon dioxide. This innovation meant that vertebrates possessing amniotic eggs could reproduce far from water, opening vast new territories for colonization and removing a major constraint on terrestrial life. The earliest amniotes, vertebrates producing amniotic eggs, appear during the Carboniferous, with the oldest confirmed fossils dating to approximately 320 million years ago. Hylonomus, discovered in fossilized tree stumps in Nova Scotia, Canada, represents one of the earliest known reptiles, measuring about 20 to 25 centimeters in length with a lizard-like body plan. This small animal likely fed on insects and other arthropods in the forest understory, using its sharp teeth to capture and process prey. The presence of fully terrestrial reptiles by the mid-Carboniferous indicates that the amniotic egg had evolved somewhat earlier, perhaps in the early Carboniferous, though the exact timing remains uncertain due to gaps in the fossil record. The amniotes rapidly split into two major lineages that would dominate terrestrial vertebrate evolution thereafter: the synapsids and the sauropsids. Synapsids, characterized by a single temporal opening in the skull behind the eye socket, would eventually give rise to mammals, though the Carboniferous synapsids bore little resemblance to modern mammals and are often called mammal-like reptiles, though that term is imprecise. Early synapsids like Archaeothyrus from the late Carboniferous resembled lizards in general appearance, but showed distinctive skull features that marked them as synapsid rather than true reptiles. These early forms were likely insectivores or small carnivores feeding on invertebrates and possibly other small vertebrates. Sauropsids, the lineage that includes all modern reptiles and birds, also diversified during the Carboniferous. Early sauropsids split into several major groups, including the ancestors of modern lizards, snakes, turtles, and crocodilians, as well as extinct groups and the lineage that would eventually produce dinosaurs, though dinosaurs themselves would not appear for another 80 million years. The Carboniferous sauropsids were generally small animals, mostly under 50 centimeters in length, occupying ecological niches as predators of insects and other small animals. Amphibians, though no longer the only terrestrial tetrapods, remained diverse and abundant during the Carboniferous. Unlike their modern descendants, which are mostly small animals, Carboniferous amphibians included some impressive giants. Proterogyrinus, from the early Carboniferous, reached lengths of about 2 meters and likely spent much of its time in water, using its powerful jaws to catch fish and other aquatic prey. Later forms like Archaeops from the late Carboniferous and early Permian could exceed 2 meters in length and possessed robust skulls with numerous sharp teeth, suggesting a predatory lifestyle. These large amphibians likely hunted along waterways and in the swamps, preying on fish, smaller amphibians, and possibly even early reptiles. Around 305 million years ago, near the boundary between the Mississippian and Pennsylvanian subdivisions of the Carboniferous period, a dramatic ecological crisis struck the tropical coal forests. This event, called a Carboniferous rainforest collapse, resulted from climate change toward drier, more seasonal conditions. The collapse fragmented the continuous tropical forests into isolated patches, separated by more arid landscapes. This habitat fragmentation caused extinctions among plant and animal species adapted to stable wet conditions, particularly affecting amphibians that required permanent water for reproduction. The giant arthropods, which had thrived in the humid forest environments, also declined, though the relationship between the rainforest collapse and arthropod size reduction remains debated. The surviving organisms in the post-collapse world included many amniote reptiles, which were less dependent on standing water due to their amniotic eggs and more efficient water conservation through their scaly skins. This gave amniotes an advantage in the drier environments, and they began diversifying more rapidly during the late Carboniferous and especially the subsequent Permian period. The stage was set for reptile dominance of terrestrial ecosystems and the eventual rise of the groups that would produce dinosaurs. By the close of the Carboniferous approximately 299 million years ago, Earth had been transformed yet again. The swamp forests continued in tropical regions but were no longer as extensive or continuous. Amniote reptiles were diversifying and spreading into new environments. The supercontinent Pangaea was nearly fully assembled, creating the largest landmass in Earth's history and setting the stage for the dramatic climatic and biological changes of the Permian period. Ahead lay the rise of spectacular synapsids, the evolution of increasingly diverse reptilian lineages, and ultimately, the worst mass extinction in Earth's history, an event so catastrophic it would nearly end complex life entirely before opening the door for dinosaurs to eventually emerge and dominate the planet. The Permian period opened approximately 299 million years ago, with Earth's landmasses locked into the largest supercontinent in the planet's history. Pangaea, whose name means all lands, stretched from pole to pole, creating a single vast landmass surrounded by the global Panthalassa Ocean. This continental configuration produced extreme climate conditions unlike anything in the modern world. Coastal regions experienced relatively moderate temperatures moderated by oceanic influences, but the vast interior, thousands of kilometers from any coastline, developed extreme seasonal temperature swings and aridity. Monsoon circulation patterns dominated, with wet summers when moisture-laden winds blew inland and bone-dry winters when air masses moved toward the ocean. These conditions created environments ranging from lush coastal forests to harsh interior deserts, setting the stage for remarkable evolutionary innovations among terrestrial vertebrates. The assembly of Pangaea through the collision of major continental blocks was largely complete by the early Permian, though some final adjustments continued. The collision of Gondwana with Euramerica created the massive Appalachian and Hercynian mountain chains, forming highlands that rivaled modern mountain ranges in scale. These mountains altered atmospheric circulation patterns, creating rain shadows that intensified aridity in continental interiors. The sheer size of Pangaea meant that many terrestrial organisms lived their entire lives thousands of kilometers from the nearest ocean, in environments where seasonal droughts could last months and water sources were scarce. This continental configuration would persist through the Permian and into the subsequent Triassic period, profoundly influencing the evolution of life. The synapsids, the lineage that would eventually give rise to mammals, underwent explosive diversification during the early Permian and came to dominate terrestrial ecosystems in ways that would not be matched by their mammalian descendants until after the dinosaurs' extinction 66 million years ago. These creatures, often imprecisely called mammal-like reptiles, were neither mammals nor reptiles in the modern sense, but rather represented a distinct evolutionary radiation exploring body plans and ecological strategies that presaged many mammalian features. The synapsids possessed a single temporal opening in the skull behind the eye orbit, a defining characteristic that distinguishes them from the sauropsids, true reptiles, which have different skull architectures. This skull fenestration provided attachment points for powerful jaw muscles, allowing synapsids to develop increasingly sophisticated chewing and biting capabilities. Pelycosaurs, an informal grouping of early synapsids, dominated early Permian terrestrial ecosystems across what is now North America and Europe. These animals ranged in size from small insectivores just a few centimeters long to massive predators and herbivores exceeding 3 meters in length. The pelycosaurs were distinguished from later synapsids primarily by skeletal features, particularly primitive characteristics in their limbs, skulls, and teeth. They retained sprawling limb postures similar to modern lizards, with their legs extending out to the sides rather than positioned underneath the body as in more advanced synapsids and mammals. This posture limited their locomotion somewhat but proved adequate for the ecological niches they occupied during the early Permian. Dimetrodon, perhaps the most recognizable pelycosaur, has become iconic despite being frequently misidentified as a dinosaur in popular culture. This impressive predator reached lengths of up to 3.5 meters and weighed approximately 250 kilograms in the largest species. Dimetrodon possessed a massive sail on its back, formed by elongated neural spines extending upward from the vertebrae and covered with skin richly supplied with blood vessels. The function of this sail has been debated extensively, with thermoregulation being the most commonly proposed explanation. The sail's large surface area and vascular network would have allowed rapid heat absorption when oriented toward the sun, enabling Dimetrodon to warm up quickly in the morning and achieve active body temperatures before its prey and competitors. Alternatively, or additionally, the sail may have served display functions for attracting mates or intimidating rivals, or possibly both thermoregulation and display functions simultaneously. The jaws of Dimetrodon reveal sophisticated predatory adaptations. Unlike most early tetrapods that possessed relatively uniform teeth, Dimetrodon had differentiated dentition with multiple tooth types serving different functions. Large canine-like teeth at the front of the jaws could puncture and hold struggling prey, while smaller serrated teeth along the sides could slice through flesh. This dental differentiation, called heterodonty, represents an important evolutionary innovation presaging the complex dentitions of later synapsids and eventually mammals. The jaw muscles, attached to the expanded temporal opening in the skull, generated powerful bite forces allowing Dimetrodon to tackle substantial prey, including large amphibians and other synapsids. As an apex predator in early Permian ecosystems of what is now Texas and Oklahoma, Dimetrodon would have played ecological roles similar to modern large carnivores. Edaphosaurus, a close relative of Dimetrodon that also possessed a prominent back sail, pursued an entirely different ecological strategy as a herbivore. This distinction makes Edaphosaurus one of the earliest known high-fiber herbivorous vertebrates, adapted for consuming tough plant material. The teeth of Edaphosaurus differ dramatically from the sharp, differentiated teeth of Dimetrodon, instead forming broad, peg-like structures suitable for grinding plant matter. Additional patches of teeth on the palate, roof of the mouth, provided crushing surfaces for processing vegetation. The digestive tract was presumably elongated to allow extended fermentation of plant material by gut microbes, similar to modern herbivorous mammals, though direct evidence of soft tissue anatomy is absent from fossils. Edaphosaurus reached lengths of approximately 3 meters, and would have spent considerable time feeding on the ferns, seed ferns, and other Permian vegetation that grew in riparian zones and lowland forests. The sails of both Dimetrodon and Edaphosaurus showed remarkable convergent evolution, two distantly related lineages independently evolving similar structures, suggesting strong selective pressure favoring this morphology. The sails varied in structure between the two groups. Dimetrodon's sails were relatively smooth and streamlined, while Edaphosaurus sails bore distinctive crossbars perpendicular to the main spines, creating a more complex structure. If thermoregulation was indeed the primary function, this would indicate that both predators and herbivores benefited from enhanced temperature control in early Permian environments where daily temperature fluctuations may have been substantial. The evolution of thermoregulatory structures in these early synapsids foreshadowed the eventual evolution of endothermy, internal heat generation, in the mammalian descendants, though the pelycosaurs themselves remained ectothermic, relying on external heat sources to regulate body temperature. Other pelycosaurs occupied varied ecological niches across early Permian landscapes. Ophiachodon, a semi-aquatic predator reaching lengths of 3 to 3.5 meters, possessed an elongated skull with numerous sharp teeth, suited for catching fish and amphibians in rivers and lakes. Unlike Dimetrodon and Edaphosaurus, Ophiachodon lacked an enlarged sail, instead having relatively short neural spines. This suggests different thermoregulatory strategies, or perhaps less need for rapid heating in its aquatic habitats where water temperatures remain more stable than air temperatures. The limbs of Ophiachodon showed adaptations for swimming, and fossil trackways suggest these animals were comfortable both in water and on land, filling ecological roles similar to modern crocodiles. Smaller pelycosaurs included insectivores and omnivores that hunted invertebrates, and possibly consumed plant material. Cassia, a barrel-chested herbivorous pelycosaur reaching lengths of about 1.5 meters, possessed proportionally small limbs and a massive rotund body housing an enlarged digestive system for processing plant matter. The body proportions of Cassia, with its tiny head, short limbs, and enormous trunk, created an almost comical appearance, but this body plan efficiently allocated internal space for the fermentation chambers necessary to extract nutrients from fibrous vegetation. The success of herbivorous pelycosaurs like Cassia and Edaphosaurus demonstrated that vertebrates had solved the challenge of plant eating, establishing terrestrial herbivory as a viable ecological strategy that would be exploited by countless lineages thereafter. By the Middle Permian, around 270 million years ago, a new group of synapsids began displacing the pelycosaurs. These therapsids, meaning beast faces, showed numerous anatomical advances over their pelycosaur ancestors. The legs of therapsids moved increasingly underneath the body rather than sprawling to the sides, improving locomotor efficiency and endurance. The skull structure became more sophisticated, with expanded temporal openings allowing larger, more powerful jaw muscles. The teeth showed even greater differentiation, with distinct incisors, canines, and post-canine teeth serving specialized functions. Herbivore possessed a thick skull with a domed forehead, legs positioned more vertically under the body than in pelycosaurs, and a massive trunk housing the digestive system. The teeth were simple pegs suitable for cropping vegetation but not for extensive chewing. Apparently, these animals swallowed plant material whole or with minimal processing and relied on gut fermentation to break down the tough plant fibers. The success of massive herbivorous therapsids demonstrated that vertebrates could achieve large body sizes on plant-based diets, presaging the later evolution of gigantic herbivorous dinosaurs, though the dinocephalians themselves went extinct by the end of the Middle Permian. Gorgonopsians emerged during the Middle Permian and would become the dominant predators of the Late Permian immediately before the catastrophic in-Permian extinction. These therapsids were specialized carnivores with elongated, saber-like canine teeth that could reach extraordinary proportions. The largest Gorgonopsians, such as Inostrancevia from Russia, exceeded 3.5 meters in length with skulls measuring 40 centimeters or more. The massive canine teeth, which could extend 8 to 12 centimeters beyond the jawline, functioned like daggers for stabbing prey. The jaw mechanism allowed these animals to open their mouths to remarkable gape angles, possibly approaching 90 degrees, enabling the canines to clear the lower jaw and be driven into prey with full force. Behind the canines, smaller serrated teeth cut through flesh. This dental apparatus made Gorgonopsians fearsome predators capable of taking down prey as large as or larger than themselves. The Dicynodonts, another therapsid lineage, evolved during the Middle Permian and would become extraordinarily successful as herbivores. These creatures ranged from small burrowing forms the size of rats to massive browsers exceeding 3 meters in length. The name Dicynodont means two dog teeth, referring to the pair of tusks that projected downward from the upper jaw in many species. The remainder of the dentition was typically absent, replaced by keratinous beak similar to that of modern turtles. This beak and tusk arrangement proved highly effective for cropping and processing vegetation. The body plans of Dicynodonts were robust and often barrel-shaped, with powerful limb muscles positioned to support substantial body weight. By the late Permian, Dicynodonts had become the dominant herbivores across most terrestrial ecosystems, filling ecological roles analogous to modern ungulates like cattle, antelopes, and hippopotamuses. True reptiles, the sauropsids that would eventually give rise to dinosaurs, remained relatively minor components of Permian ecosystems while synapsids dominated. Early reptiles of the Permian were generally small animals, mostly under 50 centimeters in length, occupying ecological niches as insectivores and small predators. However, this apparent insignificance belied the evolutionary innovations occurring within sauropsid lineages. During the Permian, the reptiles split into two major groups, the parareptiles, which would eventually decline and mostly go extinct, and the diapsids, which possessed two temporal openings in the skull and would give rise to all later major reptile groups including dinosaurs, pterosaurs, crocodilians, lizards, snakes, and birds. The early Permian diapsids were small and superficially lizard-like, but they carried within their lineages the genetic potential for the spectacular radiations that would occur after the Permian catastrophe cleared the ecological stage. The climate of the Permian period underwent significant changes from beginning to end. The early Permian inherited the late Carboniferous Ice Age, with substantial ice sheets covering the southern portions of Gondwana near the South Pole. Evidence for this glaciation includes glacial deposits, drop stones and marine sediments, and glacial striations on bedrock across what are now South America, Africa, India, Australia, and Antarctica, all portions of the ancient supercontinent Gondwana. The Ice Age persisted through the early Permian before gradually waning during the Middle Permian as global temperatures rose. By the late Permian, ice sheets had largely or completely disappeared, and global climate had shifted toward greenhouse conditions with minimal temperature gradients between equator and poles. The interior of Pangaea experienced extreme aridity due to its distance from oceanic moisture sources. Vast deserts covered much of the continental interior, particularly in equatorial regions where descending air in the Hadley circulation suppressed precipitation. Evaporite deposits, thick layers of salt and gypsum formed by evaporation of restricted water bodies, occur widely in Permian rocks from continental interior regions, documenting the arid conditions. The modern Sahara Desert, covering roughly 9 million square kilometers, provides only a pale comparison to the megadeserts that likely dominated Pangaea's interior, which may have encompassed 20 million square kilometers or more of virtually lifeless sand and rock. Along the coastal margins of Pangaea and in upland areas that captured orographic precipitation, more hospitable conditions allowed diverse ecosystems to flourish. Forests of gymnosperms, sea plants including conifers and seed ferns, replaced the lycophyte-dominated Carboniferous coal swamps, which had declined as climate became drier and more seasonal. These gymnosperm forests could tolerate drier conditions than the moisture-dependent lycophytes, and their seeds provided better protection for embryos and allowed dispersal across less continuously wet environments. Ginkgos, cycads, and various extinct groups diversified alongside the conifers, creating forest communities of moderate diversity. The understory vegetation included ferns, horsetails, and various smaller gymnosperms, while the forest floor supported communities of arthropods, small reptiles, and increasingly diverse synapsids. Freshwater ecosystems in the Permian supported diverse communities of fish, amphibians, and aquatic or semi-aquatic reptiles. Lungfish, which had evolved during the Devonian, persisted in Permian rivers and lakes, using their lungs to survive in waters that became oxygen-depleted during dry seasons. Coelacanth, lobe-finned fish that would later become infamous as living fossils when discovered alive in modern oceans, were diverse and common in Permian freshwater and marine environments. Large temnospondyl amphibians, distant relatives of modern frogs and salamanders, occupied predatory niches in Permian waterways, some reaching lengths of 3 to 4 meters with broad, flattened skulls filled with sharp teeth for catching fish and other aquatic prey. These amphibians remained confined to aquatic or semi-aquatic lifestyles, unable to compete with the more terrestrially adapted synapsids and reptiles on land. Insect diversity continued expanding during the Permian, though the giant forms of the Carboniferous had declined as oxygen levels dropped from their Carboniferous peak of 35% toward lower values. The Permian saw the first appearance of several modern insect orders, including true bugs, Hemiptera, thrips, Thysanoptera, and beetles, Coleoptera. The evolution of beetles, which would eventually become the most diverse animal order on Earth with over 350,000 described species today, began during the Permian with relatively primitive forms. The diversification of plant-eating insects created selective pressure on plants to evolve defensive compounds and physical protections, driving coevolutionary dynamics between plants and their herbivorous insect consumers that continue shaping terrestrial ecosystems today. By the late Permian, around 255 to 252 million years ago, terrestrial ecosystems had achieved remarkable complexity and diversity. Synapsids dominated, with numerous species of carnivorous gorgonopsians, herbivorous dicynodonts, and various other therapsid lineages occupying ecological roles across different body sizes and habitats. True reptiles remained present but secondary in ecological importance. Amphibians persisted in aquatic environments, but had been largely displaced on land. Insects, spiders, and other arthropods provided abundant prey for small vertebrates and fulfilled crucial roles as herbivores, decomposers, and predators. The forests, though different in composition from modern woodlands, created complex habitats with vertical structure and diverse microenvironments. This thriving world stood on the brink of catastrophe. Volcanic activity in what is now Siberia was about to unleash one of the largest volcanic events in Earth's history. The Siberian Traps eruptions that would pump enormous quantities of carbon dioxide, sulfur dioxide, and other gases into the atmosphere and trigger a cascade of environmental disasters. The synapsids that had dominated terrestrial ecosystems for tens of millions of years would be devastated. The dicynodonts, gorgonopsians, and most other therapsid lineages would be nearly or completely wiped out. Marine ecosystems would suffer even worse, with 96% of marine species perishing. The Great Dying, as it would come to be known, would bring Earth's Permian chapter to a horrific close and in doing so, finally clear ecological space for the true reptiles, the diapsids, to rise to dominance. The therapsids that survived the extinction, primarily a few lineages of cynodonts, small, advanced therapsids with increasingly mammal-like characteristics, would persist and eventually give rise to true mammals during the subsequent Triassic and Jurassic periods. But in the immediate aftermath of the extinction, it would be the diapsid reptiles, including the archosaurs, the group containing crocodilians, dinosaurs, and pterosaurs, that would seize the opportunity. The world that the dinosaurs would inherit was being forged in the fires of the Permian extinction, and that apocalyptic transition would determine the character of terrestrial ecosystems for the next 180 million years until another catastrophic extinction closed the age of dinosaurs and finally allowed mammals their turn at dominance. Approximately 252 million years ago, Earth experienced the most catastrophic mass extinction in the history of complex life. The Permian Triassic extinction event, colloquially known as the Great Dying, eliminated an estimated 96% of all marine species and 70% of terrestrial vertebrate species. Entire ecosystems collapsed. Dominant groups that had ruled for tens of millions of years vanished completely. Unlike the relatively rapid extinctions caused by asteroid impacts, this catastrophe unfolded over hundreds of thousands of years, creating a protracted nightmare of environmental deterioration that pushed life to the brink of complete annihilation. The synapsid-dominated world of the late Permian, with its gorgonopsian predators and dicynodont herbivores, will be utterly transformed, clearing the ecological stage for the eventual rise of archosaurs and dinosaurs. The primary driver of this apocalypse was volcanism on a scale almost incomprehensible. In what is now Siberia, massive eruptions began releasing enormous volumes of basaltic lava across the landscape. These were not eruptions from a single volcano, but rather flood basalts, lava welling up from extensive fissures in the Earth's crust and spreading across vast areas in flows that could extend for hundreds of kilometers. The Siberian Traps, as this volcanic province is now called, ultimately covered an area of approximately 7 million square kilometers, with basalt layers reaching thicknesses of 3 to 4 kilometers in some locations. The total volume of erupted material exceeded 4 million cubic kilometers, making it one of the largest volcanic events in Earth's history. The eruptions occurred in pulses over a period of roughly 600,000 to 1 million years, with the most intense activity concentrated in the first few 100,000 years and coinciding precisely with the main extinction pulse. Dating of the volcanic rocks using uranium-lead radiometric methods on zircon crystals has established that the eruptions began approximately 252.3 million years ago, exactly matching the timing of the extinction event recorded in marine sediments worldwide. This temporal correlation, combined with the unprecedented scale of the volcanism, establishes the Siberian Traps as the primary trigger for the catastrophe, though the mechanisms by which the eruptions caused such devastation were complex and multifaceted. The immediate effects of the eruptions involved the release of massive quantities of gases into the atmosphere. Volcanic emissions included carbon dioxide, sulfur dioxide, hydrogen sulfide, hydrogen chloride, and various other compounds. The carbon dioxide release alone was staggering, Estimates suggest the eruptions may have injected 30 to 100,000 gigatons of carbon dioxide into the atmosphere over the course of the eruptive period. To put this in perspective, human industrial emissions since the beginning of the Industrial Revolution total approximately 2,000 gigatons, meaning the Siberian traps released 15 to 50 times that amount. The atmospheric carbon dioxide concentration, which had already been elevated during the late Permian, climbed to extreme values possibly exceeding 3,000 to 4,000 parts per million, compared to approximately 400 parts per million today. The sulfur dioxide emissions created immediate short-term cooling through a mechanism understood from modern volcanic eruptions. When sulfur dioxide reaches the stratosphere, it reacts with water vapor to form sulfate aerosols, tiny particles that reflect incoming solar radiation back into space, cooling the planet. Large modern eruptions like Mount Pinatubo in 1991 injected roughly 20 million tons of sulfur dioxide into the stratosphere and cooled global temperatures by approximately half a degree Celsius for 1 to 2 years. The Siberian Traps eruptions, operating on a scale thousands of times larger and persisting for hundreds of thousands of years, would have created repeated cooling episodes, each lasting several years following major eruptive pulses. This volcanic winter effect would have been devastating for photosynthetic organisms, reducing sunlight levels and disrupting food webs. However, the sulfate aerosols fell out of the atmosphere within a few years after each eruptive pulse, while the carbon dioxide remained for hundreds of thousands of years, accumulating progressively. The long-term effect was therefore extreme greenhouse warming despite the periodic volcanic winter episodes. Paleoclimate reconstructions based on oxygen isotope ratios in fossil shells and teeth indicate that both ocean and atmospheric temperatures rose dramatically during the extinction interval. Tropical ocean surface temperatures, which had been approximately 25 to 30 degrees Celsius during the late Permian, climbed to 35 to 40 degrees Celsius, or possibly even higher during the peak of the crisis. Land temperatures in equatorial regions may have exceeded 50 degrees Celsius during summer, approaching or exceeding the physiological tolerance limits of most terrestrial vertebrates. The warming had cascading effects throughout Earth's climate system. The temperature gradient between equator and poles decreased substantially as polar regions warmed more than the tropics, weakening the atmospheric circulation patterns that drive wind systems and ocean currents. The reduced temperature gradient slowed or disrupted the thermohaline circulation, the global ocean conveyor belt-driven temperature and salinity differences that transports heat and nutrients throughout the world's oceans. When this circulation weakened or shut down, the oceans became stratified, with warm, less dense water sitting atop cooler, denser deep water, and minimal mixing between the layers. This stratification had deadly consequences for marine life. The eruptions also directly contaminated the environment with toxic compounds. When the basaltic lavas encountered the thick sequences of evaporite deposits, coal beds, and organic-rich sediments that underlay portions of Siberia, the heat caused combustion and thermal decomposition of these materials. Coal combustion released additional carbon dioxide, mercury, and toxic organic compounds. Evaporite heating released chlorine and fluorine gases. The interaction between magma and organic-rich sediments generated enormous volumes of methane, a greenhouse gas approximately 30 times more potent than carbon dioxide over century timescales. Some estimates suggest that methane releases from the Siberian eruptions may have contributed as much to warming as the carbon dioxide emissions, creating a dual greenhouse gas assault on the climate system. The warming oceans began losing their capacity to hold dissolved oxygen, creating vast oxygen-depleted dead zones. The solubility of oxygen in seawater decreases as temperature increases. Warmer water simply cannot hold as much dissolved gas as cooler water. Simultaneously, the stratification of the water column prevented oxygen-rich surface waters from mixing with deeper layers. The combination meant that oxygen concentrations in the deep ocean and even in many shelf environments declined toward zero. Evidence for widespread ocean anoxia comes from black shale deposits rich in organic carbon found in sedimentary rocks spanning the Permian-Triassic boundary on multiple continents. These black shales indicate that organic matter accumulated on the seafloor without being consumed by aerobic decomposition, possible only when oxygen levels are extremely low or absent. Even more deadly than simple anoxia was the development of euxinic conditions, waters containing not just zero oxygen, but also dissolved hydrogen sulfide, a compound toxic to most organisms. Under normal conditions, sulfate-reducing bacteria in marine sediments produce hydrogen sulfide, but the compound is quickly oxidized by oxygen in the overlying water and never accumulates. When oxygen disappeared from the water column, hydrogen sulfide from bacterial activity in sediments could diffuse upward into the water column and accumulate to toxic concentrations. Additionally, in anoxic water columns, sulfate-reducing bacteria can thrive throughout the water rather than being confined to sediments, producing hydrogen sulfide at even higher rates. Evidence for widespread euxinia during the Permian-Triassic boundary comes from biomarker molecules produced by photosynthetic sulfur bacteria, organisms that thrive only when hydrogen sulfide is present in sunlit surface waters. The hydrogen sulfide may have even escaped from the oceans into the atmosphere in some regions. In modern oxygen-rich oceans, any hydrogen sulfide that reaches the surface is quickly oxidized. But in the depleted oxygen conditions of the in-Permian oceans, hydrogen sulfide could have reached the atmosphere, particularly where upwelling brought deep euxinic waters to the surface. Atmospheric hydrogen sulfide would have been toxic to terrestrial organisms and would have damaged the ozone layer, increasing ultraviolet radiation reaching Earth's surface. This ozone destruction mechanism has been proposed as an explanation for the high extinction rates among terrestrial organisms during the Great Dying, though direct evidence for atmospheric hydrogen sulfide release remains limited. Ocean acidification added another stress to marine ecosystems. The massive carbon dioxide injection into the atmosphere meant that carbon dioxide dissolved into surface ocean waters in enormous quantities. When carbon dioxide dissolves in seawater, it forms carbonic acid, which dissociates to release hydrogen ions, lowering the pH and increasing acidity. Ocean acidification affects organisms that build shells or skeletons from calcium carbonate, as the increased acidity makes it more difficult to precipitate calcium carbonate and could even cause existing shells to dissolve. Coral reefs, which had recovered somewhat following earlier Permian extinction pulses, were devastated during the in-Permian event. Many groups of shell-forming organisms, including brachiopods, mollusks, and various plankton, suffered disproportionately high extinction rates, consistent with acidification stress. The timeline of the extinction reveals a complex, multi-phased catastrophe rather than a single instantaneous die-off. The main extinction pulse occurred rapidly in geological terms, within perhaps 60,000 years based on high-resolution dating of boundary sections, but this rapid event still represented thousands of generations for most organisms, during which environmental conditions deteriorated progressively. Some evidence suggests an initial extinction pulse affecting marine organisms, followed by terrestrial extinctions, and then subsequent pulses affecting different groups. The recovery period extended for millions of years, with ecosystems remaining simplified and low in diversity long after the initial crisis passed. The extinction selectivity provides insights into the killing mechanisms. Size-selective extinction occurred among terrestrial vertebrates, with large-bodied forms suffering higher extinction rates than small animals. This pattern suggests that physiological stress from high temperatures played a major role, as larger animals have lower surface area to volume ratios and greater difficulty dissipating heat. Among marine organisms, heavily calcified forms like corals and many brachiopods suffered disproportionately, pointing to acidification and carbonate saturation state changes as important factors. Organisms living in restricted environments like reefs or requiring specific water chemistry conditions generally fared worse than mobile generalists that could migrate or tolerate varied conditions. The Great Dying eliminated numerous dominant groups that had shaped ecosystems for tens of millions of years. Among marine organisms, trilobites, those iconic arthropods that had survived multiple earlier extinctions dating back to the Cambrian over 300 million years earlier, finally went extinct, with not a single species surviving into the Triassic. Tabulate and rugose corals, the major reef-building organisms of the Paleozoic, disappeared completely, and reef ecosystems would not recover for millions of years until new coral groups evolved. Eurypterids, the giant predatory sea scorpions that had prowled Paleozoic seas, vanished. Many groups of brachiopods went extinct, with only a handful of lineages surviving to rebuild diversity in subsequent periods. On land, the synapsid-dominated ecosystems collapsed. The Gorgonopsians, those fearsome saber-toothed predators that had been apex carnivores of the late Permian, went entirely extinct. Not a single species survived. The dicynodonts, which had been the dominant herbivores across most terrestrial ecosystems, suffered catastrophic losses, with only one or two lineages surviving the extinction. The diverse communities of large herbivorous and carnivorous therapsids were winnowed down to a handful of small-bodied survivors. The world that had been ruled by synapsids for tens of millions of years was suddenly emptied of most of its inhabitants, leaving ecological niches vacant in ecosystems simplified to a degree unprecedented since the colonization of land. The survivors of the Great Dying offer crucial insights into what allowed some organisms to persist through conditions that killed most life. Lystrosaurus, a medium-sized dicynodont roughly the size of a pig, became extraordinarily abundant in the immediate aftermath of the extinction, with some fossil assemblages from the earliest Triassic consisting of 95% or more Lystrosaurus remains. This creature possessed several adaptations that may have aided its survival: a semi-fossorial lifestyle with strong forelimbs adapted for digging burrows, which would have provided refuge from extreme surface temperatures, a generalist herbivorous diet allowing it to subsist on whatever vegetation remained, and possibly a relatively wide physiological tolerance for varied environmental conditions. The dominance of Lystrosaurus in earliest Triassic ecosystems worldwide demonstrates how a single hardy generalist species can proliferate when competitors are eliminated. Among the true reptiles, the sauropsids, survival rates were somewhat higher than among synapsids, possibly because many sauropsids were small-bodied and may have had different physiological characteristics. The archosauromorphs, the group that would eventually give rise to crocodilians, dinosaurs, and pterosaurs, survived extinction as small, often semi-aquatic forms. Procolophonids, small reptiles resembling robust lizards, persisted and diversified in the Triassic. Various groups of early diapsid reptiles made it through, though often with substantial losses. Importantly, the surviving sauropsid lineages found themselves in a world largely emptied of the large synapsids that had dominated most terrestrial ecosystems, creating evolutionary opportunities that the archosaurs in particular would exploit during the subsequent Triassic period. The recovery of life following the Great Dying proceeded slowly and unevenly. The earliest Triassic ecosystems, spanning roughly the first 5 million years after the extinction, showed extremely low diversity compared to the late Permian. Fossil assemblages from this interval are often dominated by just a few disaster taxa, opportunistic species that could tolerate the harsh conditions and proliferate in the absence of competitors. Coal formation, which had been common during the Permian when forests were extensive, essentially ceased for several million years during the earliest Triassic, indicating that terrestrial plant communities had been devastated. The absence of coal deposits, called the coal gap, extended for approximately 10 million years before forest ecosystems recovered sufficiently to begin accumulating peat that would form coal. Marine ecosystems showed similarly protracted recovery. Reef ecosystems remained absent for approximately 8 to 10 million years, representing one of the longest reef gaps in the Phanerozoic fossil record. When reefs finally began rebuilding in the Middle Triassic, they were constructed by entirely new groups of organisms, particularly scleractinian corals, which are the ancestors of modern reef-building corals and were only distantly related to the rugose and tabulate corals that had dominated Paleozoic reefs. The taxonomic composition of marine communities changed fundamentally, with new groups rising to prominence to fill ecological roles previously occupied by extinct lineages. By the Middle Triassic, approximately 245 to 240 million years ago, ecosystems had recovered substantially in terms of diversity and complexity, though they looked dramatically different from their Permian predecessors. On land, archosaurs were diversifying into multiple lineages including the ancestors of crocodilians, the flying pterosaurs, and significantly, the dinosauromorphs, the group from which true dinosaurs would emerge. Large predatory Rauisuchians, heavily armored Aetosaur, and various other archosaur groups filled ecological niches previously occupied by synapsid carnivores and herbivores. The cynodonts, advanced therapsid synapsids with increasingly mammal-like characteristics, persisted as generally small animals that would eventually give rise to true mammals, but they would not regain ecological dominance for another 180 million years. The Great Dying marked the definitive end of the Paleozoic era and the Permian world. The ecosystems that had developed over the preceding 300 million years since the Cambrian Explosion were fundamentally restructured. The extinction cleared away the dominant groups and reset evolutionary trajectories, creating opportunities for lineages that had previously been minor components of ecosystems. For the archosaurs in particular, the post-extinction Triassic world represented an open landscape of available niches and reduced competition. Within 30 million years of the Great Dying, by approximately 230 million years ago, the first true dinosaurs would appear in the Middle to Late Triassic. These early dinosaurs were small, bipedal predators and omnivores, unremarkable in the diverse archosaur-dominated faunas of their time. But they carried within their lineages the potential for the spectacular evolutionary radiation that would make dinosaurs the dominant terrestrial vertebrates for the next 165 million years, until their own catastrophic extinction at the end of the Cretaceous period. The world the dinosaurs inherited had been forged in the fires and poisons of Earth's worst catastrophe, and that crucible had determined which lineages would have the opportunity to shape the Mesozoic era. The early Triassic period opened approximately 252 million years ago, with the planet struggling to recover from the worst catastrophe in the history of complex life. The ecosystems that greeted the new era bore little resemblance to the diverse, thriving communities of the late Permian. Simplified food webs dominated by a handful of disaster-tolerant species stretched across barren landscapes where forests had once flourished. The oceans, depleted of oxygen and poisoned by hydrogen sulfide, supported only scattered populations of hardy survivors. Global temperatures remained punishingly high, with tropical regions experiencing summer highs that may have exceeded 50 degrees Celsius, conditions approaching the upper limits of vertebrate physiological tolerance. Yet from this devastation, life would slowly rebuild, and in doing so, would set the stage for the most spectacular evolutionary radiation of terrestrial vertebrates Earth had yet witnessed, the age of dinosaurs. The supercontinent Pangaea dominated early Triassic paleogeography, creating environmental conditions unlike any in the modern world. The massive landmass stretched from the North Pole to the South Pole, encompassing virtually all of Earth's continental crust in a single interconnected block. The Panthalassy Ocean, a vast body of water larger than all modern oceans combined, surrounded Pangaea on all sides.